GCE Advanced Level Chemistry Practical Series, Experiment number 1. Properties of cathode rays. Experimental observation. The aim of this experiment is to acquire the necessary skills and knowledge to identify components in an electrical circuit used to operate a cathode ray tube, and to observe and explain properties of cathode rays. Now students, in Unit 1, we discuss the different subatomic particles that are seen in atoms, and we talk about the discovery of electron, and the discovery of electron revolves around Crookes tube or cathode ray tube. So it is essential for you to know how to operate a cathode ray tube, or it is essential for you to know what actually takes place inside a cathode ray tube. So the main objectives of this experiment are very clear. We have to learn the different components of the electrical circuit that we use to operate the cathode ray tube, and there are certain properties that we can observe of cathode ray tubes within a laboratory setup. We can observe that the cathode rays travel in a straight line by placing an opaque object along the path of the cathode rays. This can be done in the lab. So today in this experiment we'll be talking about the theory part as well. We can place a lightweight pedal wheel in the path of the cathode rays to see if cathode rays can move this pedal wheel. We can subject the cathode rays into a magnetic field and electric field and observe the behavior of the cathode rays. So students, based on these observations, we can further discuss the properties of cathode rays. So the main objective of today's experiment are these. So now let's move on to the next slide. So let's take a look at our introduction here. The electric discharge through gases. Sir William Crookes conducted experiments demonstrating the ability to discharge electricity through gases by passing an electric current through them. So Sir William Crookes, you can see the image of the scientist here. He was one of the first scientists to carry out experiments to try and conduct electricity through gases. And when he was conducting these experiments, he observed that at lower pressures and really high voltages, electricity can be passed through a gas. And in honor of his findings, we now actually name the cathode ray tubes Crookes tubes. So this is Sir William Crookes, who actually conducted experiments to try and find out if electricity can be passed through gases. Crookes' experiment revealed that connecting two electrodes to a high voltage source resulted in a heated cathode emitting invisible radiation. The radiation was not visible to the eye. He saw when he connected two electrodes to a really high voltage, and when you're trying to conduct electricity through a gas that is at a low pressure, he was able to observe an emission of invisible radiation. Although the rays were unseen, their presence was detected by causing a low pressure gas to glow and inducing fluorescence in other substances. This emitted radiation was termed cathode rays. Now students, although we say that this radiation is invisible, when this radiation comes into contact with low pressure gases, see these low pressure gases, upon contact with this invisible radiation, gave out a glow. So then we were able to understand that there is an invisible radiation produced from the cathode. And at the same time, we saw that certain fluorescence materials like zinc sulfide was able to produce a very clear glow upon contact with these cathode rays. Since these rays are seemingly emitted through the cathode, these rays were named cathode rays. They were not getting emitted through the anode. We saw actually initially he started noticing a glow around the cathode, and this glow started traveling towards the anode gradually. Since the glow initiated near the cathode and then moved towards the anode, it was concluded that the cathode rays, or these invisible rays that are produced, are actually getting produced near the cathode. So we call these cathode rays, right? So the invisible radiation that he observed that are getting produced near the cathode was named cathode rays. Who discovered cathode rays? Who actually discovered this phenomena first? Mainly Sir William Crookes. The main requirements needed in order to conduct electricity through gases are high voltage and low pressure. Now, these two are very important, students. When you are learning about cathode rays, you need to learn to produce cathode rays. What are the main requirements? First of all, you need to have a Crookes tube or cathode ray tube which is capable of lowering the pressure within the tube. So we can have any gas within this tube. However, the pressure of the gas within the tube should be lowered. So we have to have a low pressure inside the tube, and apart from that, between the electrodes that are present within this tube should have a really high potential difference, or really high voltage should be applied to these two electrodes. So these are the two main requirements when carrying out our cathode ray related experiments. Cathode rays will be produced and will be observed easily when the gases that are present within the cathode ray tube has a lower pressure, and when the electrodes that are present within the cathode ray tube has a high voltage applied between them. So you can see that travel to the opposite end of the tube. When cathode rays strike fluorescent material applied to this end, it glows. Now, students, we have recognized that cathode rays are essentially a beam of electrons shot out of atoms or molecules that come into contact with this negatively charged cathode. So, we have our cathode here, which is extremely negatively charged. When an atom or a molecule comes into contact with this negatively charged cathode, due to high repulsion observed between the cathode plate and the atom or the molecule's outer electrons, the electrons can get shot out of the atom. And this will happen perpendicular to the cathode surface. And after being shot out of the atom near the cathode, these electrons are going to travel in a straight line to the other end of the cathode ray tube. So as they travel, if they come into contact with the gases at low pressure, when they collide, there can be a glow that is going to be observed. This is the initial glow that Sir William Crookes observed when he was initially conducting these experiments. And if these electrons go and collide with a surface that is coated with a fluorescent material like zinc sulfide, as they collide with this surface, a green color glow will be observed. So when cathode ray particles, which are electrons essentially, when these cathode ray particles go and collide with a fluorescent material, you will observe a green color glow. So this can be used to detect the presence of cathode rays. Equipment required for this experiment. For this experiment, we would of course need cathode ray tubes. So it is in plural. The reason is we are going to be using different types of cathode ray tubes for different types of experiments. So we'll be using a variety of cathode ray tubes, all following the same principle. We have a sealed tube with a gas at a lower pressure, and we have two electrodes within the cathode ray tube that can be supplied with a high voltage. So the two main requirements of a cathode ray tube is to have two electrodes that can be supplied with a high voltage and to have a gas at lower pressure within the cathode ray tube. And to operate this cathode ray, or to complete the circuit, we would need induction coil and a connecting wires. So induction coil and connecting wires are going to be required. So the process of carrying out this experiment is given here. High voltage is applied to the cathode ray electrodes by converting alternating current from the main grid into direct current. So this is important. In the lab, what we can obtain from the main grid is alternating current. So first, we can't apply alternating current to a cathode ray tube. It will alternate the cathode and the anode multiple times within a second. So this is not going to be useful. This type of current is not going to be useful. There you can't directly apply alternating current into a cathode ray tube. So we need to convert this alternating current, which is usually referred to as AC current, into DC current. DC stands for direct current. So we can convert this alternating current into direct current. So this is done with the use of our power supply and the induction coil. And then subsequently, we can amplify its voltage through the induction coil that we have in this setup. So in this setup, we have circuitry that is capable of converting the alternating current into a direct current, as well as amplifying the voltage with the use of an induction coil. The induction coil generates a high voltage induction coil generates a high voltage around 1000 volts. So when we provide it with a smaller voltage like 230 or 250 voltage, it will convert into 1000 volts, which is then applied to the electrodes of the cathode ray tube. So like I mentioned earlier, two requirements of operating a cathode ray tube is a high voltage and a gas at low pressure within the cathode ray tube. So cathode ray tubes, modern day cathode ray tubes we get in the lab are already containing a low gas sealed within a glass tube. So it is sealed, we can't connect a vacuum pump to it. It is already sealed, but we can be sure that the sealed cathode ray tubes contain a gas at lower pressure. And the next requirement is high voltage. So we can obtain a high voltage by converting alternating current into direct current and then amplifying the voltage up to about 1000 volts with the use of a induction coil. Cathode ray tubes are instrumental in demonstrating the properties of cathode rays. There are different properties of cathode rays you should learn about. And when you are learning about these things, to demonstrate these properties, cathode ray tubes are instrumental. They are essential, especially that is why we have this experiment as the experiment number 1 in our practical series, because you need to know the properties of cathode rays, and to demonstrate the properties of cathode rays, we need to use these cathode ray tubes. Altering the trajectory of cathode rays using magnetic fields. So students, in this part of our experiment, we are going to actually observe how the path of the cathode rays will change when subjected to a magnetic field. So I told you earlier, when cathode rays come into contact with the fluorescent material, it causes the fluorescent material to glow. So students, we are going to now use a cathode ray tube that has a metal plate diagonally positioned within the cathode ray tube. So as the cathode rays come, since it is diagonally positioned, these cathode rays will definitely come into contact with the fluorescent material, because this metal plate coated with the fluorescent material is going to be placed diagonally, not parallel to the cathode rays, but diagonally at an angle to the cathode rays. So then as the cathode rays travel straight, since this metal plate coated with zinc sulfide is placed diagonally, these cathode rays will definitely come into contact with this fluorescent material. Zinc sulfide is this fluorescent material that we have plated on this metal plate. So when cathode rays come into contact with this fluorescent material, there will be a glow that can be observed. So this will allow us to see the path of the cathode rays. But the cathode surface is somewhat large. If all of the cathode rays come into the main region where the fluorescent material is present, then we can see a very clear straight line of the cathode ray path. So because of that, what we do is we block most of the cathode rays that are emitted by the cathode. How do we do this? We place another metal plate right in front of the cathode. Right in front of the cathode, we place a metal plate. And in this metal plate, we are going to have a small slit, a small rectangular slit that will allow only a beam of cathode rays to pass through this metal plate. So we have the cathode, we have a metal plate that is blocking almost all of the cathode rays, only allowing a beam of cathode rays to come out of the metal plate. So then we have another metal plate that is diagonally positioned after the initial metal plate you see. There's another metal plate that is diagonally positioned, coated with zinc sulfide, the fluorescent material. And then as this cathode ray beam comes into contact with this zinc sulfide coated metal plate, it will cause the zinc sulfide to give out a green color glow. So this will reveal the path of the cathode rays. So that is explained here, students. So in this experimental arrangement, we have a cathode ray tube containing a cathode ray tube containing a diagonally positioned metal plate coated with zinc sulfide between the two electrodes. So you can see actually over here, this region, you can see a metal plate that is diagonally positioned, not parallel to the cathode rays, but at an angle to the cathode rays. And this plate is positioned between the two electrodes. Adjacent to the cathode, you can see this is the cathode, and very close to the cathode, do you see there is another metal plate with a small slit in the middle that will allow only a beam of cathode rays to come into the region where the metal plate with the zinc sulfide is present. So another metal plate with a small slit was positioned adjacent to the cathode, enabling only a focused beam of cathode rays to enter the region where the zinc sulfide coated plate was present. So when you are having, if this is our cathode rays are going to be produced like so. However, there's going to be a metal plate right in front of it. This is going to block most of the cathode rays, but there's going to be a small slit in the middle of this metal plate, which will allow a nice beam of cathode rays to pass through. Most of the other cathode rays will not make it through the plate. Only the cathode rays that are aligning perfectly with this slit will pass through the slit and go into the next section of the cathode ray tube. And if you observe the second section of the cathode ray tube from the top, right? So we will be taking a look at the top view of the cathode ray tube. So when you are observing the cathode ray tube from the top, this is going to be your cathode, this is going to be your anode, and right over here is the metal plate that is going to be blocking all of the cathode rays that are produced, except for the cathode rays that are aligning perfectly with the slit in this metal plate. And apart from that, students, we are going to observe a metal plate that is diagonally positioned like this. So when cathode rays, when they pass through this metal plate, they definitely will come into contact with our diagonally positioned metal plate coated with zinc sulfide or fluorescent material. So we will see a glow. Now this is the top wave. Keep in mind, this is the top wave. This is our top wave. So only a few of the cathode rays will make it through this metal plate with the slit here, and then they will form a nice beam of cathode rays, and this cathode ray beam will come into contact with the fluorescent screen here, because this fluorescent screen is going to be placed at an angle to the cathode rays. So then they definitely will come into contact with the fluorescent screen. And due to this, if you now actually move on to the side view of it, due to this, you will very clearly observe the path of the cathode rays. So let's make this our side view. This is side view. And in the side wave, we will see that there is a metal plate here with a small opening, and then we have the fluorescent screen, which is diagonally positioned. And we can see a lot of cathode rays produced here, but only a small beam of cathode rays will enter this region. And that beam of cathode rays, since they are coming into contact with this fluorescent screen that is coated with zinc sulfide, is going to show a very clear green color glow. Zinc sulfide coated metal plate. So students, this is how we can reveal the path of the cathode rays. We place a fluorescent screen diagonally like so, and make sure we only take a very clear beam of the cathode rays into that section where the fluorescent screen is present. And then when you turn on the cathode ray tube, you will observe that a very clear green color glow will be observed on the places where the cathode rays come into contact with the fluorescent material. So this area will grow green in color because the cathode ray is come into contact with the fluorescent material there. Right. Now, what happens? Now, this is more of a 3D diagram. You can see how the fluorescent screen is present here, how the cathode is present here, how there is a small metal plate blocking most of the cathode rays, allowing only a small portion of the cathode rays to come out as a beam of cathode rays. And as you can see here, when you bring a magnet close to this cathode rays, the path of the cathode rays deviated. Actually, earlier on, the cathode rays traveled in a straight line. Earlier on, the cathode rays traveled in a straight line. From here to here, they would have traveled in a straight line like so. We will use a thicker line so that you can see it clearly. Cathode rays would have traveled in a straight line like this. But when you bring a magnet, a north pole of a magnet, you can see the cathode rays get deflected a little bit. So this indicates that in the presence of a magnetic field, cathode rays can get deflected. They move away from the magnetic field. So upon passing through the slit, the rays travel in a straight line towards the anode, striking the zinc sulfide screen and appearing as a distinctive thick green colored line. So after passing through this slit, you can see a distinctive straight line actually being observed on the zinc sulfide metal plate, or metal plate coated with zinc sulfide. But if you bring a magnet, then you can see this straight line can no longer be observed. The path of the cathode rays actually bend. So let's move on to that. Cathode rays initially seem to travel in a straight line. However, introducing the north pole of a magnet between the cathode ray tube electrodes reveal noticeable curvature in the previously straight path. So if you bring a magnet between the two electrodes, or if you bring a magnet into the path of the cathode rays, then you observe that cathode rays are now not traveling in a straight line. We can see a very noticeable deviation from that straight line path. So students, over here, if you observe, have the cathode rays gotten attracted towards the north pole? Does it show any indication that the cathode rays are trying to come towards the north pole? Or is it indicating that in the presence of the magnet, north pole of the magnet, earlier on, students, the cathode rays traveled in a straight line like so, but now when you brought the magnet near it, the cathode rays are traveling in a curved path, actually not towards the north pole. However, the path of the cathode rays have gotten deflected. So in a magnetic field, students, these cathode rays, in a magnetic field, cathode rays get deflected perpendicular to the magnetic field. If you have magnetic field like so, if the initial trajectory of cathode rays can be indicated with this, we'll use red color because it's quite visible. The green color, I'm not sure whether you can see very clearly. So if cathode rays initial path was like this, straight, what happens when you try to send or when you subject the cathode rays into a magnetic field is the cathode rays get deflected. Bear with me a second, students. We'll still use red. The cathode rays will get deflected perpendicular to the our magnetic field. So when I say perpendicular, they're not getting attracted to the south pole or the north pole. That is not what is happening. These cathode rays, they travel in the same plane, but they will get deviated along the same plane. Are perpendicular to the magnetic field. So the magnetic field is pointing downwards. The plane that is perpendicular to the magnetic field is this, right? So if the magnetic field is pointing downwards, the perpendicular plane to the magnetic field would be this. So cathode rays will travel, and when it comes into contact with the magnetic field, it will deviate or deflect perpendicular to the magnetic field, right? So it is not getting attracted to the north pole or to the south pole. Instead, it is actually repelled in a way perpendicular to the magnetic field. Is it clear, students? So if you again observe a top view from the top, let's say we can only see the north pole of the magnet at that point. If this is the top wave, of course, then if you are looking from the top, the south pole of the second magnet cannot be seen. So the initial path of the magnetic field, or initial path of the cathode rays, should be like this, right? Now I'm writing it in dashed lines because we have now introduced a magnetic field, so this path will no longer be present. But when you are having a magnetic field, cathode rays will get deflected like this. So this straight line and this curved line, they're in the same plane. They're in the same plane. And that plane is perpendicular to the magnetic field. So when you're talking about deflection over here, keep in mind, students, that cathode rays do not get attracted. Cathode rays do not get attracted to the north or the south pole. They instead get actually repelled by the magnetic field. They get repelled by the magnetic field. And the cathode rays trajectory is going to be altered perpendicular to the magnetic field. If the magnetic field is pointing downwards in a plane that is perpendicular to the magnetic field, cathode rays will get deflected. So that is something you need to keep in mind. North pole or a south pole of a magnet cannot attract cathode rays. Instead, they will get deflected by the north pole or south pole of a magnet. So as you can see in this diagram, when the north pole of a magnet is brought near the cathode rays, they get deflected downwards like this in a plane that is perpendicular to the magnetic field. And if you switch magnets poles, particularly by bringing the south pole near the tube, change in the direction of the course opposite to the original path is observed. So the direction of this deflection is going to change. So over here we have still given an image where the north pole is brought here. So if you change it to the south pole, if you change this to the south pole and this to the north pole, right? At that point, students, you will observe that this trajectory will no longer be like this. Instead, even the trajectory will change. This trajectory will be moving upwards. The path of the cathode rays will change. If north pole is causing the trajectory to move downwards, south pole will do the opposite. South pole will cause the path of the cathode rays to move upwards. Cathode rays do not exhibit attraction to magnetic poles. Instead, they change direction perpendicular to the magnetic field. This behavior confirms charged nature of cathode rays. Now, students, this type of deflection is seen in only charged particles. This type of behavior under a magnetic field can only be seen in charged particles. So this confirms that cathode rays are charged. If it gets deflected in a perpendicular plane to the magnetic field, this particular behavior is also observed in charged particles. So that would mean the cathode rays are charged particles. Right now, when we were discussing cathode rays, we learned that cathode rays are a stream of electrons, and we know electrons are charged. But at the time when the cathode rays were discovered first, we did not know whether they were charged or not. So when scientists were conducting these experiments, they were trying to learn more about the nature of cathode rays. So when they were carrying out this experiment, they observed in a magnetic field they get deflected in this particular manner, which led them to conclude that cathode rays are in fact charged particles, because only a beam of charged particles will alter their trajectory in the presence of a magnetic field. So this deflection took place in a perpendicular plane to the magnetic field, which confirmed that these particles that are seen in the cathode rays are in fact charged. In the next slide, we are going to carry out yet another experiment. So we do know that cathode rays are traveling in a straight line. So we needed to confirm this with the use of another type of cathode ray tube we have over here. So students, we have a cathode ray tube that has an opaque object placed along the path of the cathode rays. So along the path of the cathode rays, we have placed an opaque object. You can see we have the cathode here and the anode here. So anode is not directly opposite to the cathode here, because we learned earlier when you are producing cathode rays, the cathode rays are traveling in a straight line away from the cathode. So cathode rays are emitted perpendicular to the surface of the cathode, and these cathode rays are traveling in a straight line. Actually, cathode rays are shot out of the cathode and they are traveling in a straight line. So to make sure that they travel in a straight line, to actually confirm this assumption, we can actually place an opaque object, a metal object that cathode rays can't pass through, and then observe if a shadow will be casted in the opposite end of the cathode ray tube. So that is exactly what we have done here. We have a cathode here, and we will be turning on the cathode ray tube along with this opaque object in the middle. So then what happens is, as cathode rays pass through, due to the presence of opaque object in the middle, certain amount of cathode rays can't pass through that area, casting a shadow at the back of the cathode ray tube. So when cathode rays come into contact with the glass at the back of this cathode ray tube, it will cause a green color glow. You can observe this very clearly in the lab as well. And the shape that is placed along its path will be very clearly seen in the shadow as well. So the shadow that is produced is going to have very sharp edges. So this indicates that the cathode rays did in fact travel in a straight line. If they were not traveling in a straight line, this type of very sharp shadow or sharp edged shadow cannot be produced. You can't produce this type of very sharp edged shadow if the cathode ray particles did not travel in a straight line. And the shadow will not have the same shape if they were not traveling in a straight line. So let's take a look at what is written here. To illustrate that cathode rays travel in a straight line from the cathode to the anode, cathode ray tube fitted with a metal cross is used. So this metal cross is raceable. Actually, you can raise it up or place it down. So when you are starting the experiment, it will be placed down so that all the cathode rays will pass through all the way to the back of the cathode ray tube, and this entire region will be glowing in green. But after a while, we can lift up the metal cross. So then we can see a very sharp edged shadow is getting formed at the back of the cathode ray tube. A metal cross is positioned between two electrodes of the cathode ray tube. When the tube is activated with a high voltage supply, a clear image of the cross with sharp edges appears in the glass wall of the anode side. Right. In addition to this shadow, the remaining parts of the glass will emit a green glow. This test confirms that cathode rays travel in a straight line from the cathode towards the anode. Right, students? So this test was mainly carried out to investigate whether the cathode rays actually travel in a straight line. And we saw, since they were traveling in a straight line, when an opaque object is placed right along the path of the cathode rays, we can see a shadow with sharp edges at the back of the cathode ray tube's glass. So when the cathode rays go and collide with the glass of the cathode ray tube, or the back end of the glass of the cathode ray tube, you can see a green color glow happening there. And if cathode rays do not come into contact with the glass, you will not be observing a green color glow. So that is why there's going to be a dark shadow here. The rest of the area, you can see a green color glow. So this indicates, students, that cathode rays were traveling in a straight line. So whenever you are asked this question, why was this particular experiment was carried out, you have to mention that this particular experiment was carried out to show that cathode rays travel in a straight line. And how did we come to that conclusion? When an opaque object was placed along the path of the cathode rays, it was capable of producing a shadow with sharp edges, indicating that cathode rays have traveled in a straight line. Now, students, let's move on to the next slide. Change in trajectory of cathode rays in an electric field. The same cathode ray tube used to test the cathode rays in a magnetic field was employed for this purpose. A zinc sulfide screen is positioned between the electrodes in the tube, and a cover plate near the cathode blocks the path of the cathode rays, directing them through a small hole or small slit. Consequently, the zinc sulfide screen displays a thick green line indicating the cathode ray beam traveling towards the anode. If no green light is observed upon turning on the cathode ray tube, switch the positive and the negative terminals of the potential source to induce a glow or a shine from the cathode rays. Now, in this experiment, we are trying to observe whether cathode rays will change its direction or its path when exposed to an electric field. So students, the same cathode ray tube that we used to observe the behavior of cathode rays under a magnetic field is going to be used here, right? So we have a metal plate right in front of the cathode, covering most of the cathode rays that are going to be emitted by the cathode, and this metal plate is going to have a slit that will only allow a beam of cathode rays to enter the part where you have a metal plate coated with zinc sulfide. And then when you turn on the cathode ray tube, students, you have to observe a thick green color line on the fluorescent screen. If you can't observe this type of thick green light, that is because you might have connected the two electrodes into the power source incorrectly. In the power source, in the induction coil, you have the option of switching the two electrodes potentials. So you can actually switch between positive and negative charge of the two electrodes. So you can switch it and see if you then observe a thick green color line across the fluorescent screen. If you don't see a thick green color line across the fluorescent screen, that could mean your two things actually. That could mean that the voltage that you have provided across the electrodes is not sufficient, or it could also mean that you have not connected the negative terminal of the power source to the cathode of the cathode ray tube, right? So by switching the two terminals and correctly connecting the negative terminal of the power source to the cathode and the positive terminal of the power source to the anode, you can see this thick green color line being formed. Now, we have to arrange this experimental setup according to this illustration that is given here, and we have to make sure that we configure the circuit to ensure a negative charge on the copper plate here. So we have a negatively charged copper plate, and we bring this negatively charged copper plate towards our cathode ray tube, which is now fixed to the fluorescent screen at the back. So we can see the path of the cathode rays. As we bring this negatively charged plate close to the cathode rays, we see that cathode rays are going to get deflected downwards. If you bring the negative charged copper plate from the top, the cathode rays are going to get deflected downwards. If you bring the negative charge plate from the bottom, they will get deflected away from the negative charge plate upwards. So this indicates that the cathode rays are getting deflected in an opposite direction to the negatively charged copper plate. So at this point, we have a few observations, students. Now we have conducted our third experiment here. The first experiment, we brought a magnetic field and we learned that the cathode rays are charged particles, a beam of charged particles. And then we saw if you actually place an opaque object, that a very crisp or very clear, sharp-edged shadow of that image is going to be casted on the back of the cathode ray tube. So this observation actually gives us another piece of information. That is, now in the first experiment we saw magnetic field proved that cathode rays are charged, and in this experiment we can tell what sort of charge is present on cathode rays. Now keep in mind, students, again, this is a reminder, when these experiments were carried out, scientists didn't know the actual charge of cathode rays. Although now you know how cathode rays are formed, and then you know cathode rays are basically a stream of electrons, and so you know cathode rays are negatively charged. But when they initially discovered cathode rays, they didn't know the charge of cathode rays. But they could find out by bringing a negatively charged plate close to the cathode rays, and they saw cathode rays were trying to get away from this negatively charged plate. Actually, cathode rays were getting repelled by the negatively charged plate. So therefore, cathode rays were actually going down in this instance away from the negatively charged plate. If a positively charged plate was brought, then you see the cathode rays are getting attracted towards the positively charged plate. If a negatively charged plate was brought close to the cathode rays, they will get deflected away from the negatively charged plate. So this observation confirms that cathode rays are charged, and even gives us an idea of the charge of the cathode rays. They are negatively charged. By using the negatively charged plate to investigate the behavior of cathode rays in electric field, an interesting phenomena was observed. Upon activating the cathode ray tube, the green light observed to move towards the side opposite to the negatively charged plate. So basically, when you bring the negatively charged plate from the top, cathode rays will move downwards, away from the negatively charged plate. This observation confirms the presence of repulsion in the presence of negative electric field, leading to conclusion that the cathode rays are negatively charged. Cathode rays are negatively charged. Further experimentation where cathode rays pass through a strong electric field reveals a change in their path as they are attracted to the anode. This reinforces the deduction that cathode rays are indeed negatively charged. So that means, students, if you carry out further experiments, how cathode rays behave, imagine this is the initial path of cathode rays, and you bring a positively charged plate and a negatively charged plate close to this. Right, so we'll draw that roughly here. If you bring positively charged plate and a negatively charged plate close to it, we can actually see cathode rays. You can see cathode rays getting attracted towards the positively charged plate. like so, right? So this indicates that the cathode rays are definitely negatively charged. They were getting deflected away from the negatively charged plate towards the positively charged plate. So by now we carried out 3 experiments. We saw in a magnetic field, cathode rays get deflected in a plane that is perpendicular to the magnetic field, indicating the cathode rays are charged. In electric field, cathode rays were getting attracted towards the positive charged plates but was repelled by the negatively charged plates. This indicates that the charge of the cathode rays is negative. And we carried out another experiment to see if the cathode rays are traveling in a straight line always by placing an opaque object and observing a very clear, sharp-edged shadow of the opaque object at the back of the cathode ray tube. So these are the 3 main experiments we carried out. And then we move on to another experiment where we are trying to show that the cathode rays have particle properties. Keep the cathode ray tube with the pedal wheel in a horizontal position and activate the cathode ray tube. So students, what you see over here is another type of cathode ray tube. I told you in the beginning of this experiment we are going to be using few different types of cathode ray tubes. We have already seen 2 types. We saw the first type where we have a cathode ray tube with a fluorescent screen inside. And then we saw another cathode ray tube with a raceable metal cross inside it. And this is the third type of cathode ray tube with a very light pedal wheel inside. So in the cathode ray tube, there's a very lightweight pedal wheel on 2 tracks actually. These tracks are made of glass. So on this 2 tracks, we have a pedal wheel that can easily move back and forth. But we are going to place this cathode ray horizontally on the table, making sure that it is not slanted, it is perfectly leveled with the table. So now we can see you have the cathode here, you have the cathode here, you have the anode here. So the cathode rays are going to be formed in this region. You can see cathode rays are traveling from the cathode towards the anode, like so. And the pedals of this pedal wheel are going to be actually encountering these cathode rays as the pedals extend onto the path of the cathode rays. Pedals are actually along the path of the cathode rays. So as pedals protrude like this along the path of the cathode rays will come into contact with the pedal, and if cathode rays have particle-like properties, then when they hit the pedal wheel, the pedal should move. So that is what is happening here, students. So when you place this pedal wheel along the path of the cathode rays and then you turn on the cathode ray tube, you will observe this pedal wheel is starting to move away from the cathode towards the anode, because cathode is the place where the cathode rays are produced. And then as cathode ray particles move towards the anode, if a pedal is present along that path, then when the cathode ray particle hits, this pedal should move. So as we conduct this experiment, we actually see this very lightweight pedal wheel spin and move towards the anode. Now this indicates that our cathode ray particles or cathode rays have kinetic energy, right? So they have particle-like nature. So let's take a look at this text here. The pedal wheel rotates and moves towards the anode. Now switch the negative and the positive terminals. In this case, the pedal wheel moves in the opposite direction. So students, in the previous example, we can see In the induction coil, you have the option of switching the charges on the two electrodes. So in this diagram, you can see the system is configured for the left-hand side electrode to be the negatively charged electrode. So we have labeled it the cathode, and the right-hand side electrode is going to be a positively charged electrode. We have labeled it the anode. But with the use of the induction coil, we can switch these charges. We can convert this left-hand side electrode to have a positive charge and right-hand side electrode to have a negative charge. At that point, the cathode and the anode will switch. So this can be done with just a small turn of a switch in the induction coil. So when you do that, students, you will see quickly these two anode and the cathodes will change. And when that happens, imagine initial setup, we have the pedal wheel moving from the cathode to the anode. In this case, the cathode is the left-hand side electrode, anode is the right-hand side electrode, and the pedal wheel will be moving towards the anode from left to right. But as it reaches the right-hand side, we can switch the two electrodes. So when you do that, this side will be the cathode, right? At that point, this end will be the cathode when you switch, and this will be the anode. So at that point, this pedal wheel will stop and again will start moving from cathode to the anode. So no matter how many times you switch back and forth, changing the cathode and the anode, alternating between these two electrodes, no matter what you do, you will observe this pedal wheel will always move from cathode to the anode, right? So it doesn't matter where the cathode is. Cathode could be the left-hand side electrode or the right-hand side electrode. The direction of the pedal wheel is always going to be from the cathode to the anode. So this indicates that the cathode ray particles or cathode rays are emitted actually by the cathode. Let's take a look at the second paragraph here. The collision of cathode ray propels the pedals from the cathode to the anode, indicating the kinetic energy required for this propelling action was provided by cathode rays. So for the pedal wheel to move from the cathode to the anode, now pedal wheel was initially still. For it to spin and move towards the anode, it needs to acquire kinetic energy. Otherwise, it wouldn't all of a sudden start to move. So from where did this pedal wheel acquire this kinetic energy? It was acquired by the cathode rays. When the cathode ray particles came and collide with the pedals of the pedal wheel, some amount of the energy or kinetic energy in the cathode rays or cathode ray particles were transferred into the pedal wheel, causing the pedal wheel to spin and have certain amount of kinetic energy. And then this spinning took place due to the transfer of kinetic energy of the cathode ray particles into the pedal wheel. Placing a light pedal wheel between the two electrodes in a cathode ray tube results in the movement of the pedal wheel in the tube is activated when the tube is activated. This experiment confirms that the cathode ray possess kinetic energy. So that means when it comes to talk about kinetic energy, it has a 1 over 2 mv to the power 2 mass into velocity square. So you can see that if the pedal wheel can obtain kinetic energy, that would mean the cathode ray particles had kinetic energy. So this is the equation for kinetic energy. So students, if cathode ray particles have kinetic energy, that would mean cathode rays have a velocity as well as a mass. So these are not just rays, these are particles as well. So we can now actually conclude that cathode ray particles have a velocity as well as a mass based on this observation. Based on the observed movement and kinetic energy, it can be inferred that cathode ray possess mass and velocity. Therefore, cathode rays exhibit particulate properties. Since momentum is equal to m multiplied by v, cathode rays should also have momentum. Cathode rays should also have momentum. So we saw earlier cathode rays had kinetic energy that was displayed by the pedal wheel spinning from cathode to the anode. So that means cathode ray particles had kinetic energy. Kinetic energy can be explained by an equation, half m or mass into velocity to the power 2. So cathode ray particles have kinetic energy means they would have a mass as well as a velocity. Anything that has a mass and a velocity has momentum as well. So we can say cathode ray particles have momentum as well. Properties of cathode rays do not depend on the nature of the gas. Properties of cathode rays do not depend on the nature of the gas. In any cathode ray obtained from any gas, charge Q divided by mass m value is the same. This particular value is going to be the same. This is the charge to mass ratio of any cathode ray particle obtained from any gas is going to be the same, no matter whether you use helium, hydrogen, chlorine, neon, whatever the gas that you use inside the cathode ray tube. If you are able to measure the charge to mass ratio of these cathode ray particles, then at that point you would observe this charge to mass ratio of any cathode ray particle produced with the use of any gas is going to be identical. And this value, charge to mass ratio value of cathode ray particles or cathode rays is going to be 1.759 into 10 to the power 8 coulombs per gram. Coulombs per gram. Or else you can communicate it this way as well, 1.759 into the power 11 coulombs per kilogram. Both of these are correct. This suggests that negatively charged particles with a mass are present in every gas are identical. So this concludes that in any gas there is a negatively charged particle with a specific mass, and each of these particles, regardless of what type of gas we are observing, each of these particles that are present in all of these gas is going to be identical. So although initially this was carried out for gases, we later learned that these negatively charged particles are present in all elements. So then this particular particle is what we currently know as electron. This was named E, or electron. So students, in any gas that they observed the charge to mass ratio of any gas is going to be identical, and it was the numerical value of it was found by J.J. Thomson. So for finding this numerical value and for identifying that there is a negatively charged particle that is identical in every element, he was awarded the honor of discovering the electron. Electron was experimentally discovered by J.J. Thomson. Electron was experimentally discovered by J.J. Thomson, and this charge to mass ratio of electrons were given by J.J. Thomson. And these particles that were discovered was named electrons. J.J. Thomson is credited with the physical discovery of electron through his investigation of cathode rays. And then he communicated the charge to mass ratio based on those experiments and observations and his charge to mass ratio related information that he provided. He was able to conclude that in every element we have this negatively charged particle with a mass, and he named them electrons. So students, the discovery of electron was done by J.J. Thomson. In an electron, the charge to mass ratio, often given as Q divided by M, sometimes given as E divided by M. Majority of the time it's Q. Q usually stands for charge. So Q divided by M or E divided by M is going to be the charge to mass ratio of these particles. So in an electron, charge to mass ratio is 1.759 into 10 to the power 11 coulombs. Now coulomb, C, stands for the unit for the measurement of charge. So we have 1.759 into 10 to the power 11 coulombs per kilogram. So this particular finding was done by J.J. Thomson. And later on, a scientist named R.A. Millikan was able to find the actual charge of an electron. He was able to find the charge of an electron through a test called oil drop test. We say Millikan's oil drop test. In this test, he was able to discover the smallest charge that can be found in any amount of charge. Actually, he noticed that any amount of charge he observed through his experiment was a multiplication of a very specific small charge. So all of the charges he observed, different types of charges he observed, was always a multiplication of a specific value, and that value, he concluded, is the smallest electrical charge that can exist, and that charge is the charge of an electron. So that charge is going to be given as 1.602 into 10 to the power minus 19 coulombs. Very small charge, extremely small, 10 to the power minus 19 coulombs. So electron's charge was discovered by R.A. Millikan. Electron was discovered by J.J. Thomson. Electron's mass to charge ratio was discovered by J.J. Thomson. Then with the use of this charge, since we know the mass to charge ratio of an electron, we can find out the mass of an electron. So you can see we have done that. We know the mass to charge ratio is this, right? And we know the relationship between mass to charge ratio, charge divided by mass. So instead of charge being denoted with Q, we now know the mass, or we now know the charge, not mass. We now know the charge of an electron. So instead of Q, we can substitute that value with the actual numerical value. And when you do that, only unknown here is M. So we can now find out M by rearranging the equation. When you do that, mass of an electron happens to be 9.107 into 10 to the power minus 31 kilograms. For a cathode ray particle, the charge is going to be 1.602 into 10 to the power minus 19 coulombs. So cathode ray particles are basically, students, electrons. So this charge that you see in a cathode ray particle is the same as the charge of an electron, 1.602 into 10 to the power minus 19 coulombs. And the charge to mass ratio, now this is what J.J. Thomson found out. The charge was found out by R.A. Millikan. And J.J. Thomson found out the charge to mass ratio, and that is going to be 1.759 into the power 11 coulombs per kilogram. And using the charge that Millikan found out and the charge to mass ratio that J.J. Thomson found out, we were able to calculate the mass of an electron, which is going to be 9.107 into 10 to the power minus 31 kilograms. 10 to the power minus 31 kilograms. This is an extremely small mass. Now compared to a proton, we say the mass of an electron is negligible. You can see why. Because the mass of an electron is in 10 to the power minus 31 kilogram range. So students, these are the details that you should keep in mind. Now, when you talk about electrons, protons and neutrons, we have to have a rough idea about who discovered each of these subatomic particles. So electrons were initially, actually the initial idea of electrons was given by Johnstone G. Stoney. So this scientist actually proposed the initial idea of electrons. He proposed the initial idea of electrons. He actually proposed that just like matter has the smallest indivisible particle called atom, when it comes to electrical charge also there is the smallest charge that can be there, and all of the other charges that you see will be multiplications of this smallest charge. So after proposing the idea of this smallest charge, Stoney suggested a name for it called electron. Although he didn't have experimental evidence to prove the presence of an electron, he is the one who initially proposed the idea of electrons. So initial idea of electron is Stoney's. And then discovery of electrons. Now J.J. Thomson conducted many experiments revolving around the cathode ray tube. He observed the properties of cathode rays, and he also communicated the mass to charge ratio of cathode rays, finally leading to the discovery of electrons. So the discovery of electrons were done by J.J. Thomson. And the charge of electrons were discovered by R.A. Millikan through his oil drop test. So these are the information that you should keep in mind about electrons and its history. The initial idea of electrons was by Johnstone G. Stoney. Discovery was by J.J. Thomson, and charge of electrons were discovered by R.A. Millikan. And then we have protons here. Protons discovery is by Rutherford, and neutron discovery is by James Chadwick. So in this particular experiment, our main focus is on electrons, but however, knowing these two will also be important. So in an atom, we know the mass of the atom is going to be concentrated on the nucleus. So the mass of the atom is going to be containing the neutrons and protons. These are subatomic particles that have a heavier mass compared to the electron. So electrons' mass compared to these neutrons and protons are going to be negligible, and these heavier subatomic particles are going to be concentrated in the middle of the atom called the nucleus, and around the nucleus you will have electrons. Atoms are composed of subatomic particles known as electrons, protons, and neutrons. Electrons, protons, and neutrons. And we learn about their main charge and masses here. So each of these subatomic particles have their own symbol. Electrons are signified by E, protons by P, and neutrons by N. Now, when it comes to electron, the relative charge is -1. When you're comparing the charges of electrons and protons, it has -1 charge. And proton has the same magnitude of charge, but an opposite charge. So protons are going to be +1. Electrons are -1. So they have their relative charges. That means not their exact charge. Exact charges are different, but their relative charge is going to be -1 and +1. When you're comparing their charges to one another, they have the same magnitude of charge, but opposite charges. The size of the charge is the same, but charges are opposite. So if you take a look at the absolute charge of an electron, it is -1.602 into 10 to the power minus coulomb. Right? So this is the magnitude of charge, and the sign is showing the type of charge, negative charge. And the absolute charge of a proton is the same magnitude as the absolute charge of an electron, 1.602 into 10 to the power minus 19 coulombs. So the magnitudes are the same, but you can see the charges are opposite to one another. So electrons are negatively charged, protons are positively charged. So when you compare those two and talk about their relative charges, we say the relative charge of an electron is -1 and relative charge of a proton is +1, right? So their actual charge, absolute charge, is this. Their relative charges are these. However, neutrons don't have a charge. Neutrons don't have a charge. If you bring in their masses into this part, you will see that when it comes to electrons and protons, they have a huge mass difference. Roughly around 1840 times smaller mass is seen in electrons compared to protons. And protons and neutrons, they are quite similar in mass. Behavior patterns of subatomic particles in a magnetic field. So we have magnetic north pole and magnetic south pole here. You can see when subatomic particles like electrons, neutrons and protons, when they pass through the magnetic field, their trajectories or their paths, they get affected by the magnetic field. So we learned, students, earlier on, charged particles can get deflected in a magnetic field, and that deflection will take place along a plane that is perpendicular to the magnetic field. If the magnetic field is pointing downwards, we will have a perpendicular plane to the magnetic field, and you can see as protons and electrons pass through this magnetic field, they have gotten deflected. Keep in mind, although this diagram shows like electrons have gone up and protons have gone down, that is not what has happened here. All of these electrons, neutrons and protons, they are in the same plane, and this plane is going to be perpendicular to the magnetic field. And what has actually happened is protons have gotten deflected towards you as electrons have gotten deflected away from you in the same plane, right? So it has not gone up or down. What has happened is in the same plane, electrons have gone this way and protons have come towards you. In this diagram, that is what is explained. So in a magnetic field, this type of deviation is observed because of charged particles. So if you send a charged particle in a magnetic field like this, their trajectories are going to change, are going to get altered in the following manner. Charged particles are going to be deflected in a perpendicular plane to the magnetic field. However, you can see neutrons were not affected by the magnetic field. Why? Because neutrons do not have a charge. Both electrons and protons do carry a charge. In fact, their charges are the same in magnitude but opposite in charge. They both carry the same charge magnitude but opposite charges. As we saw earlier, their absolute charge values magnitude wise was the same, but the charges were opposite. However, protons and electrons are charged particles. That is why we see a deflection in their trajectories in the presence of a magnetic field. Electrons and protons exhibit distinct movement in magnetic field due to their electric charge. Their trajectories are affected because they carry a charge. In contrast, neutrons, being electrically neutral, do not experience a change in their trajectory in a magnetic field. So we have observed this much by analyzing this diagram. And keep in mind, students, electrons or protons are not attracted to either one of these poles of any of these magnets. What happens is that they get deflected in a perpendicular plane to the magnetic field. In a perpendicular plane to the magnetic field, they get deflected. They are not attracted to either of these north or south poles. Charged particles, they get deflected in a perpendicular plane to the magnetic field. Patterns of behaviors of subatomic particles in electric field. You can see over here in electric field what has happened. So if you take a cathode and an anode, if you have potential difference between two electrodes, and then when you send these subatomic particles through this electric field that we have over here, we can see electrons are going to be attracted towards the positively charged plate. Now, this is a direct attraction towards the plate. This is not a deviation in a perpendicular plane to the electric field. No, this is directly. The electrons are negatively charged, and as they move through, they experience a positive charge from below. So they get attracted towards that side. So the trajectory of electrons will change this way. protons, as they move through, they will experience a negative charge from above. Protons are positively charged, so they will get attracted towards the negatively charged plate. Neutrons, they are not charged. They will not feel any attraction towards either one of these plates, because why? They are neutral, they are not charged. But when we are drawing these trajectories, you can see electrons, their curvature is greater in their trajectory compared to protons. This is because protons are heavier. Their trajectories will not change as easily as electrons. Electrons are around 1840 times, roughly, lighter than protons. So electrons' trajectories have changed a bit faster compared to protons. Protons will turn slowly. So this is what happens in an electric field. Protons and electrons change direction in electric field. Electrons are attracted to the anode. It confirms that electrons or cathode rays are charged. We know electrons are negatively charged. Electrons get attracted to the positively charged anode. If you send cathode rays will also show the same behavior, because cathode rays are electron beams. Protons are repelled from the anode, right? So protons repel from anode and get attracted more towards the cathode. Protons are attracted to the cathode, so it must be positively charged. Neutrons do not change their trajectory in an electric field. This is because the neutron is electrically neutral. So as I mentioned earlier, when it comes to talking about electric field and how the subatomic particles behave, we can see electrons get attracted to the anode, protons get attracted to the cathode, and since neutrons are electrically neutral, they will not get attracted to either electric field. So keep in mind, students, when it comes to electric fields, there is an attraction shown by certain subatomic particles to either one of these, cathode or the anode. But when it comes to a magnetic field, neither of the subatomic particles will show any attraction towards any magnetic pole. Instead, what you see is a deflection of the trajectories of these subatomic particles in a plane that is perpendicular to the magnetic field. Right? So these subatomic particles are not getting attracted to either one of the magnetic poles. Instead, they're getting deflected in a perpendicular plane to the magnetic field. If electrons are getting deflected to one direction, protons will be deflected to the opposite direction. But neutrons, on the other hand, will not show any deflection in a magnetic field or in electric field, because neutrons are neutral in their charge. Charge of an electron. Johnstone G. Stoney in 1926-1912 showed through calculations that the minimum amount of electric charge of a substance is 1.602 e to the power minus 19 coulombs. This led to the introduction of the term electron for the fundamental particle of electricity, despite the absence of experimental proof of its existence at that time. So, without the presence of any experimental proof, he actually coined the term electron. He said, when it comes to any substance, the minimum amount of charge that any substance can have is 1.602 into 10 to the power minus 19 coulombs. Or he said there is a minimum charge that any substance can have, and that is 1.602 into 10 to the power minus 19. So he said when it comes to electrical charge, the minimum value is this, and that is named electron. So he is the one who brought in the word electron. So that is why when later on J.J. Thomson discovered the electron through our cathode ray experiments. The negatively charged particle with a mass was termed electron in honor of John Stone G. Stoney's discovery. A few years later, electron was physically discovered by J.J. Thomson, and a few years later, the charge of the electron was precisely determined by R.A. Millikan through his oil drop experiment. The charge of an electron was then very precisely determined by this scientist R.A. Millikan, and it happened to be minus or negative 1.602 into the power minus 19 coulombs. And this particular piece of evidence was brought forward by R.A. Millikan through his oil drop test. The unit of charge initially proposed by Stoney was named after him in recognition of his initial idea about the electron. Now we know the smallest charge that we can see in a substance is stemming from electrons. So John Stone G. Stoney is the one who actually proposed this term, electron, or the smallest charge in any substance. Now, later down the line, when we discovered electrons through cathode ray experiments, we saw the charge of it was the same charge that he proposed, or the smallest charge that can be seen in any substance. And John Stone G. Stoney was the one who proposed the idea that the smallest charge seen in any substance is named electron. So, in recognition of his initial idea about the smallest charge that can exist in matter, the smallest negatively charged particle with a mass was named electron, the term that he introduced. So, electron name and the initial idea of the electron was stemming from John Stone G. Stoney. Wave-like properties of an electron. After developing Bohr model of the hydrogen atom, scientists confirmed that under experimental condition, radiation can have both wave properties and particle properties. Wave-like properties and particle-like properties. Louis de Broglie expanded on this concept, demonstrating that under specific conditions, radiant energy can behave as a stream of particles. We later call them photons. And matter can exhibit wave properties. So later on, we come to an understanding that electrons or that certain particles can behave like waves, and waves can show particle properties as well. So this is what this particular statement talks to us about. We call this wave-particle duality. He also proposed that an electron moving around the nucleus of an atom can behave as a wave, indicating it possesses a wavelength. So this is very important. If a particle can behave like a wave, it should have a wavelength, right? So if we claim that electrons, they can behave like a wave, then we should be able to associate a wavelength with it. Additionally, he suggested that the wavelength of an electron is dependent on its mass and its velocity. He said a wavelength of the electron was mainly dependent on two things, mass and its velocity. And the equation is given here. Lambda, which is the wavelength of this electron, is equal to Planck's constant h divided by momentum p. So we can expand that and write h divided by mass into velocity. Momentum is mass into velocity. In this context of Louis de Broglie's proposal, where h is Planck's constant, the product of an object's mass and velocity is referred to as the momentum. So p is the momentum, h is the Planck's constant. So we can Since we know P is equal to mv, we can rewrite the equation this way as well. The de Broglie hypothesis is applicable to all matter, allowing any object with mass and velocity to exhibit characteristic matter wave. However, for normal-sized objects like golf balls, the associated wavelength is extremely small and thus challenging to observe. In contrast, for electron with its significantly smaller mass, this wave-like behavior is more pronounced and observable. Now, if you go back to the equation over here, students, Planck's constant is a constant, right? Planck's constant is a constant. So we'll write this equation. Lambda is equal to Planck's constant divided by mass into velocity. Since Planck's constant h is a constant numerical value, we can write lambda of a particle with momentum is directly proportional to 1 over mass into velocity, or in other words, lambda is inversely proportional to mass and lambda is inversely proportional to the velocity. So in large objects, when they are moving at a specific velocity, since the mass value is quite high, lambda value will be small. But we saw the mass of electron is in 10 to the power minus 31 kilogram range. So students, this mass value is extremely small. So therefore, the lambda value is more pronounced and observable. So that is why when it comes to electrons specifically, such small particles, we are able to observe their wave properties, and we can associate its wavelength with electrons very easily because electrons have a very small mass. So we can actually calculate a wavelength for an electron moving at a specific velocity. Evidence that cathode rays have wave properties. Diffraction patterns. One evidence supporting the wave properties of cathode rays is the observation of diffraction patterns. When cathode rays pass through crystal lattice, they exhibit diffraction patterns similar to those observed with light waves passing through diffracting material. This phenomenon suggests that cathode rays undergo diffraction, supporting their wave-like nature. So just like light gets diffracted when it passes through a crystal lattice, we can see even cathode rays also get diffracted. So light rays are electromagnetic radiation, or in other words, a type of electromagnetic waves, and this similar type of behavior is observed in cathode rays as well. So they exhibit wave-like properties. The other one is de Broglie equation. The de Broglie equation, where lambda is equal to Planck's constant divided by momentum of the electron, further reinforces this idea by linking momentum of cathode ray particles to their associated wavelength. So students, this is experimentally proven that we can calculate the wavelength of a cathode ray particle or an electron with the use of that equation. So this further reinforces the idea that cathode ray particles or electrons show wave-like properties. Now this summarizes our properties of all of the cathode rays we saw here. Cathode rays, they travel in a straight line and cast shadow of the objects placed in their way. That was one of the experiments we conducted in this experiment number 1. There is momentum and has kinetic energy. In cathode ray particles, there is momentum. and kinetic energy. We saw that when you place a pedal wheel along its path. When you place a pedal wheel along its path, we observed that the pedal wheel will start to move away from the cathode more towards the anode. Cathode rays has mass and velocity. And based on the observation that I just made a little while ago, if cathode rays have kinetic energy, that would indicate cathode rays have mass as well as velocity. So therefore, it has momentum. Attracted towards the anode in an electric field, yes, cathode rays are negatively charged. Basically, cathode rays are essentially electrons, so they will be negatively charged and they are attracted to the anode. Negatively charged cathode ray particles exhibit the ability to ionize gases. Now, these cathode ray particles, students, are traveling at such high speeds. So when they encounter gas molecules or gas atoms, when they collide with these molecules or atoms, due to the high amount of energy these electrons are now possessing, when they collide with these particles, electrons from the molecule or the atom can get removed, can be knocked off of the atom or the molecule, causing them to be ionized. So ionization can happen. Negatively charged cathode ray particles exhibit the ability to ionize gases. Yes, that can take place. In a magnetic field, cathode rays deflect perpendicular to the magnetic field and are not attracted to magnetic poles. Instead, magnetic poles repel cathode rays. Very important distinction between electric fields and magnetic fields. In a magnetic field, cathode rays are deflected perpendicularly to the magnetic field. They are not attracted to either one of the magnetic poles. Cathode rays are emitted perpendicularly from the cathode surface. And in the initial parts of today's theory part of this experiment, we drew a diagram and we showed that when atoms or molecules, when they come into contact with the cathode that is seen in the cathode ray tube, due to the really high negative charge on the cathode, electrons will be shot out of the atom. Right? Atoms, electrons will be repelled really fast. So this repelling takes place in a perpendicular angle to the cathode surface. They can be produced with any gas and their properties remain independent of the gas type. So regardless of what gas you use in the cathode ray tube, the charge to mass ratio will not change of these cathode ray particles. So you can see any gas can be employed to produce cathode rays. However, their charge to mass ratio will not be altered with the use of different gases. Cathode rays are invisible, but fluorescent substances will produce a glow upon collision with the coated spot. So if you have a metal plate coated with a fluorescent material and cathode ray particles come into contact with them, there will be a green color glow observed. Cathode rays can be obtained from various gases, including hydrogen, nitrogen, chlorine, as well as noble gases like helium, neon, and etc. However, cathode ray cannot be produced in the absence of a gas in the cathode ray tube. Now, this is again another important point. If there are no gases in the cathode ray tube, at that point, students, there won't be any atoms to come into contact with the cathode plate, and there won't be any electrons repelled from the atom if there are no atoms in the cathode ray tube. So therefore, when there are no gases in the cathode ray tube, when it is a complete vacuum, at that point, you can't expect to observe the cathode rays. High potential gap should be applied across a low pressure gas to obtain our cathode rays. So students, when it comes to cathode rays, when you're trying to produce cathode rays, you have to have a really high potential difference applied across two electrodes, and you should have a container having a gas at a low pressure. So the two main requirements is a high potential difference and a low pressure. So high potential gap. So a high potential gap and a low pressure gas are a must. The speed of cathode ray particle is less than the speed of light. It is not equal to the speed of light. Speed of cathode ray particle is somewhere around 0.5 to 0.9 c. Now speed of light is usually denoted by c, and cathode ray particles have a speed ranging from somewhere around 0.5 to 0.9 the speed of light. When a lightweight object is positioned between electrodes, it moves towards the anode. Yes, we saw this in an experiment. We placed the pedal wheel. We observed the pedal wheel will start moving from cathode towards the anode. As the cathode rays or cathode ray particles strike the pedal wheel got more and more kinetic energy and started to spin and move towards the anode. Now, cathode rays had kinetic energy. As they strike the pedal wheel, some of the kinetic energy will be transferred to the pedal wheel, causing the pedal wheel to move. Placing an object between electrodes result in formation of a distinct image with sharp edges. Yes, we saw when we placed a opaque object along the path of the cathode rays, we saw the formation of a sharp edged shadow. This denoted that cathode rays are traveling in a straight line. The charge to mass ratio does not depend on the nature of the gas. Yes, this is something that J.J. Thomson found out, and he also discovered the charge to mass ratio. So this is because cathode ray particles are essentially electrons. Regardless of what gas that you include in the cathode ray, the charge to mass ratio will never change because all of the cathode rays that are produced are electrons. No matter what gas or what element is included in the gaseous form inside the cathode ray tube, the charge to mass ratio will not change. The cathode ray obtained from any gas have a charge to mass ratio of 1.759 into 10 to the power 8 coulombs per gram. So this was discovered by J.J. Thomson. Charge to mass ratio of cathode ray particles is 1.759 into 10 to the power 8 coulombs per gram. And he then later discovered that these are charged particles or particles with a negative charge and a mass. Therefore, any gas, substance, particles with negatively charged mass are identical. These particles are known as electrons. So yes, when it comes to any gaseous substance, he denoted that they have a charged mass that are identical to one another, and those were later on named electrons. Cathode ray particle is an electron. Now we come to the main point. We now know cathode ray particles are essentially just electrons. So cathode ray is a beam of electrons. Cathode ray is just a beam of electrons. Relative charge of cathode ray particle is -1. Relative charge of cathode ray particle is -1, which is the relative charge of an electron compared to a proton is -1. And the absolute charge is this, minus 1.602 into the power minus 19 coulomb. And this was found out by R.A. Millikan. The mass of cathode ray particle is 9.107 into the power minus 31 kilograms. After the discovery of the charge as well as the charge to mass ratio of an electron, we could find out the mass of an electron. Cathode ray exhibit wave properties, and using the de Broglie equation we can actually calculate the wavelength of a cathode ray particle or electron. Cathode rays have both wave and particle properties. Wavelength can be calculated from de Broglie equation. Wavelength is equal to Planck's constant divided by momentum of the electron. And then 22nd point, The value of cathode ray particles charge to mass ratio was experimentally determined by J.J. Thomson, thus proving the existence of electron. The type of radiation that helped to discover the electron is cathode rays. So, the discovery of electron is thanks to the cathode rays. J.J. Thomson discovered electrons by further investigating the cathode rays. So, the discovery of electron was mainly done due to the investigations that were carried around cathode rays. The physical discovery of electron is credited to J.J. Thomson. Physical discovery of electron is credited to J.J. Thomson. And Johnstone G. Stoney is credited with the initial idea of electron, and R.A. Millikan is credited with the discovery of the charge of the electron. So students, with this we cover few main points revolving around discovery of electron as well as cathode rays. With that students, we conclude this experiment's first part, where we discussed the theory parts revolving around experiment number 1. Now in this theory part we discussed how to operate a cathode ray tube. We looked at how cathode rays are produced, and we learned what cathode rays actually are. Cathode rays are electrons, and we learned that certain behaviors of electrons or cathode rays can be observed through different experiments we can do in the lab. So with the cathode ray tubes, with different cathode ray tubes, we can observe different properties of cathode ray tubes. So it is now time for us to actually move on into the lab and conduct these different experiments and observe different properties of cathode rays. So now students, let's move on to the lab and actually conduct this experiment. GCE Advanced Level Chemistry Practical Series Experiment number 1, demonstrating the properties of cathode rays. The aim of this experiment is to provide the necessary skills and knowledge to identify different electrical components of the cathode ray and how to handle the electrical circuitry of cathode ray tube, and to understand how cathode rays behave under different conditions. So we are going to observe the different properties of cathode rays by taking the cathode ray tubes and observing how they deflect in an electrical field and a magnetic field, and when we try to send cathode rays through an opaque object, how they behave and how it would act when we direct the cathode rays towards a pedal wheel. So now let's move on to identifying the equipment we will be using for this experiment. Now students, let's identify the equipment we will be using for this experiment. We have our induction coil. This is a voltage amplifier. So this device will allow you to amplify the voltage that you get from our normal electrical system. We normally receive about 230 volts from the main plug, and this will be able to amplify it to between 10,000 and 15,000 volts. And we have a knob over here to turn it on, off, and regulate the voltage. And there is another knob over here that will allow us to invert the potential difference between these two electrodes. We have wires to connect these electrodes to our cathode ray tube. We have a magnet. We will be using all of these cathode ray tubes. Each of these is a cathode ray tube. Now students, this specific cathode ray tube or discharge tube, it is normally referred to as a Crookes tube, as it is William Crookes who invented the cathode ray tube. So these cathode ray tubes this specific one is made specifically to observe that the cathode rays are traveling in a straight line. So we have an opaque object here at the right hand corner of this cathode ray tube, which we can fold down and raise up again. So this specific cathode ray tube will mainly be used to observe that the cathode rays that is produced here are traveling in a straight line, and it will cast a shadow at the back of this cathode ray. Apart from this cathode ray, we will be using a different cathode ray here that we have here. This specific cathode ray comes with a pedal wheel, a wheel with pedals attached to it. You can see it easily travels along the rails that is provided to this pedal wheel. And this specific cathode ray tube is going to be used to show that the cathode ray or stream of particles produced when it comes to producing a cathode ray has kinetic energy. So we are trying to show that the cathode ray particles or the stream of cathode ray particles has kinetic energy with the use of this specific cathode ray tube. Then we have, students, another cathode ray that we have over here. This is used mainly to observe the path of the cathode rays produced. So at the back of this cathode ray, at an angle, you can see there is a white color plate. So this white color plate is coated with a fluorescent material like zinc sulfide. And when cathode rays are produced from this electrode on the right hand side, a stream of cathode rays will be going towards the left hand electrode. So as cathode rays come into contact with this fluorescent material, you can actually observe the cathode rays as they illuminate a specific path along this fluorescent panel that you see over here. So we can detect the path of the cathode rays that are produced here. Cathode rays are invisible to the eye. So with the use of this fluorescent panel set up inside the cathode ray tube at an angle, we will be able to observe the path of the cathode rays. With that, we have identified the different cathode ray tubes and other equipment and circuitry we will be using for this experiment. Let's move on and conduct this experiment. Let's take a look at this induction coil. Has a few moving parts. We have here two electrodes with pointy needle-like electrodes pointing out, and we have two knobs over here. As I introduced before, what we have here is a knob to turn on and off the device, as well as to increase or reduce the voltage that this device produces. And this particular knob on the right hand side is capable of changing the charge of each of these electrodes. The negatively charged electrode is referred to as the cathode, and the positively charged electrode over here is referred to as the anode. And the cathode and the anode's positions can be switched with this device, with this knob. If you turn this knob, the cathode and the anode will be switched. If earlier this was the cathode, after turning the knob, electrode on the right hand side will turn to be the cathode. Now students, when you are handling a device such as this, you have to be very careful, because this device is capable of taking in 230 volts that is provided by our grid, and it is capable of converting it into over 10,000 volts. So we can go up to between 10,000 to 15,000 volts with the use of such device. So as you increase the voltage, there is a high risk. If you mishandle it, you can get electrocuted, which is not a desirable outcome. So students, please make sure that you are very careful around a device such as this. And as you turn on the device, make sure when you turn on the device that this knob is set to the off position. And then when you turn it clockwise, you will be increasing the voltage between these two electrodes. When you keep increasing the voltage between these two electrodes, at one point there will be a really high voltage which will allow the electrons from the cathode to jump towards the anode. So this will only happen when you increase the voltage to a significantly higher number. So when there's a really large potential difference between the two electrodes, at that point electrons can jump from the cathode towards the anode, creating a spark. So at that point, where we observe sparks being generated between these two electrodes, you will be able to come to the conclusion that there is a significantly high voltage difference or potential difference between the two electrodes. Now let's turn on the device. We have the knob over here at the off position. Now what we are going to do is we are going to slowly increase the voltage between these two electrodes, and at one point when the voltage is high enough, or when the potential difference between the two electrodes are high enough, you are going to observe sparks being generated or electrons jumping from one electrode to the other. So you can observe here from the left hand side electrode, sparks are generated and it is received by the electrode from the right hand side. So the left hand side electrode is our cathode and the right hand side electrode is our anode. So now students, we have identified what this particular device does. We know that it is capable of amplifying the voltage. We know that it is converting the alternating current that it receives into direct current, which is actually a major important point of this device, because when you are trying to conduct the cathode ray experiment, it is very crucial to have a direct current, and this device is capable of converting the alternating current that you receive from the electrical grid into a direct current. So this mainly is capable of doing three things. It can amplify the voltage from around 230 volts that it receives, and it can amplify it all the way between 10,000 to 15,000 volts, and it can convert an alternating current into a direct current. And apart from that, with the use of this knob, you can switch the cathode and the anode of this device. So these are the three main things that this device is capable of doing. Now let's move on to the cathode ray tube. Now students, what we have in front of us is a cathode ray tube. So a cathode ray tube is used to observe the cathode rays or the rays emitted by the cathode. So in this particular tube that we have over here, we have a gas at low pressure, and Usually it is hydrogen gas that we have inside the cathode ray tubes. So we have hydrogen gas at a low pressure here inside this tube. So inside this tube we have a gas at a low pressure, and we have a cathode and an anode inside this cathode ray tube. And the gas that is at a low pressure over here is going to come into contact with the cathode and start producing cathode rays. And in the theory part of this practical, I would have mentioned how the cathode rays are produced. Now, if you have hydrogen gas inside this cathode ray tube, when we provide a high voltage or high potential difference between the cathode and the anode of this cathode ray tube, the cathode will heat up a little bit. So the gas molecules, when they come into contact with the cathode, first they will turn into atoms, and afterwards, students, when these atoms collide with the cathode, electrons will jump out of the cathode, because cathode is going to be saturated with negative charge, or cathode is going to have a high negative charge. And as atoms come and collide with the cathode, electrons will be repelled from the atom. So atom's outer surface, or we have new electrons surrounding the nucleus. So the outer surface of the atom is going to consist of electrons. So when those atoms come into contact with this cathode, which is now having a really high negative charge, when these atoms come into contact with the anode, electrons from the atom will be ejected away from that. And this removal of electrons, or electrons, will be ejected perpendicular to the cathode plate. So the electrons that are removed will be moving in a straight line perpendicular to the cathode plate. So this is something that we have learned in the theory part of this experiment. I thought of reminding the same to you before we start this part of our experiment. So to test that the cathode rays are moving in a straight line, students, we have this particular design of cathode ray tube, and this particular cathode ray tube has an opaque object inside the cathode ray tube, which can be raised like this or can be lowered like this. So we will first connect this cathode ray tube into our induction coil, and we will adjust the induction coil to provide this cathode ray tube with a high voltage. And after providing a high voltage, you will observe that the back end of this cathode ray tube will start to glow with a nice green color glow. And this will indicate the cathode rays are produced, and they are traveling towards the back of the cathode ray tube and illuminating the back of the cathode ray tube as the cathode rays collide with the glass that we have over here. And as I mentioned how the cathode rays are produced, we know the cathode rays are going in a straight line. When atoms come into contact with the cathode that is now negatively charged, when the atoms come into contact with the cathode, atoms will lose electrons. Their electrons will be ejected from the atom perpendicular to the cathode plate, and those electrons will travel in a straight line and will go and knock the back end of this cathode ray tube, creating a green glow at the back of the cathode ray tube. So if you want to observe that these cathode rays are traveling in a straight line, we can raise this opaque metal object. So as the cathode rays are traveling in a straight line, if they are in fact traveling in a straight line, they will create a shadow in the shape of this opaque object. So we have a cross here. So the shadow that gets formed at the back of the cathode ray tube should look like a cross. So since you know the theory revolving around cathode ray tubes now, let's move on to the actual experiment and conduct it to see whether we get the expected observation. Students, what we have in front of us is a cathode ray tube. This is also known as a Crookes tube because this cathode ray tube was invented by Sir William Crookes, who is a physicist and a chemist who was conducting experiments to see if gases can conduct electricity. So in his attempts to experiment with gases, he created this cathode ray tube, and what he was observing was when you provide a really high voltage between the cathode and the anode of a tube like this, which is filled with gases at low temperature, he observed the formation of invisible radiation or stream of invisible particles traveling from the cathode to the anode. And these particles were formed at the cathode, so he named these particles cathode rays. And since then, since this was the device that was used to observe these invisible radiation or invisible particles that are traveling from the cathode to the anode, since this was the device that was used to observe these particles, this device was named the cathode ray tube. Since William Crookes or Sir William Crookes is the one who invented this device, this is also sometimes known as Crookes tube. So students, what happened here is that you have a glass tube that is sealed off. Inside this glass tube, students, you have a gas at a very low pressure. So this particular sealed off glass tube contains a gas at very low pressure, and we have our cathode here and we have the anode here. So if you look at this device, also have a cathode which is negatively charged and an anode over here on the right hand side which is positively charged. So if you connect the cathode of the oscillator to the cathode of the cathode ray tube and the anode of the oscillator to the anode of the cathode ray tube and close the circuit, you will be observing the formation of invisible radiation or a stream of particles that are going from cathode to the anode. And this will happen only at really high voltages. So we will have to increase the voltage with the use of this device. So as you increase the voltage at one point, you will observe invisible radiation moving from the cathode to the anode. Now, I keep telling you that there is a stream of particles or invisible radiation moving from cathode to the anode. So if it is invisible, how are we going to observe it? How do we know that this is getting formed? As these radiation or particles move from cathode to the anode, it collides with the gases that we have over here at low pressure. And as these particles come into contact with this gas, it allows the gas to glow. So you will be seeing a green color glow over here when it comes to this cathode rays being formed. This will indicate the formation of cathode rays. And to sometimes observe these cathode rays better, we will sometimes use fluorescent materials such as zinc sulfide. So if you move on to the next steps of our experiment, you will observe that we are using a fluorescent screen that will detect the cathode rays that are produced from the cathode. For the time being, you will observe when you connect this cathode ray to this device and when we start forming cathode rays, you will observe cathode rays through the glow of the gas that is found inside this tube. So now let's connect this cathode ray to this device and we'll start the machine and we'll observe the formation of cathode rays. We have two wires with crocodile clips, which we will connect to our cathode here, and we will connect the other end to the cathode here in the cathode ray tube. And then we have another wire that we can connect to our anode, and we will connect the other end of that wire to the anode of the cathode ray tube. Over here, the cathode ray tube that we have also contain a gas inside of it at a very low pressure, and we have a cathode on the right hand side. What we see over here is the cathode of the cathode ray tube, and at the bottom you can see another electrode that would be our anode. And as he was conducting this experiment, he noticed a ray of invisible radiation was formed from the cathode and was moving in a straight line towards the anode. Later on, it was discovered that this ray or invisible ray or ray of a stream of particles that were produced from the cathode were actually electrons. So now we know the cathode rays that we observe over here are electrons. But at that point, when he initially discovered them, he didn't know whether they were electrons or not. So the ray of these invisible particles that are formed over here were traveling seemingly in a straight line. And since this stream of particles or invisible radiation was formed from the cathode, these rays were named cathode rays. And since we use this device to observe these rays, this device was named cathode ray tube. So now, students, we have connected this cathode ray tube into this device. The cathode of the cathode ray tube is connected to the cathode or the negatively charged end, and the positively charged end of the power supply or the anode is connected to the anode of our cathode ray tube. Now, we are going to turn this device on, and we are going to start providing a bit of a high voltage to this cathode ray tube. And you can see, as I start providing a high voltage, there is a stream of invisible radiation traveling from the cathode straight towards the anode. Although the anode is over here, since the rays are traveling in a straight line, you can see the back end of this cathode ray is starting to glow. Now, students, although the particles that are emitted by the cathode are invisible, they are capable of colliding with the gas particles inside the cathode ray tube and allowing them to glow. Or else, if there is a fluorescent material that they come into contact with, they will allow this fluorescent material also to glow. Later on, we'll be using a different cathode ray, which is containing a fluorescent screen to identify the path of the cathode ray tube, to identify the path of cathode rays, as when cathode rays come into contact with a fluorescent material, it will allow the fluorescent material to illuminate. Over here at the back end of this cathode ray tube, you can see it is starting to glow. This is because cathode rays have been produced, and since they have traveled in a straight line, you can see the back end of this cathode ray is glowing. Now, to make sure that we understand that the cathode rays are actually traveling in a straight line, what we can do is place an opaque object, an object that will not allow cathode rays to pass through, between the cathode and the back end of the cathode ray tube. So, students, to observe that these cathode rays are traveling in a straight line, we can place an opaque object between the cathode and the back end of this cathode ray tube. And we have a metal cross lowered inside this cathode ray tube. We can raise it up and place it right in between the cathode and the back end of the cathode ray tube. So if the cathode rays are traveling in a straight line, it should cast a shadow at the back end of this cathode ray tube in the shape of this cross. So let's turn off the device first. Let's turn off the device. And let's raise this cross into an upright position. Now we have raised the cross into an upright position, as you can see over here. Now let's turn on the device and let's form some cathode rays and see whether it will cast a shadow in the shape of this cross. Now students, if you observe closely, you will be able to see a darker region, or in other words, a shadow cast on the back of this cathode ray tube due to cathode rays traveling in a straight line. As cathode rays travel in a straight line, they come into contact with this opaque object or object that will not allow the cathode rays to pass through. So therefore, a shadow in the shape of this object is casted towards the back of the cathode ray tube. You can very clearly observe the formation of a cross or formation of a shadow in the shape of a cross at the back of our cathode ray tube. Now students, we can very clearly see the shadow that is observed here when we place an opaque object along the path of our cathode rays that is produced in this cathode ray tube. So let's turn off the device. So why did we observe a shadow in the shape of this cross? The reason for observing a shadow that is having the exact shape of this cross is because the cathode rays that are produced at the cathode over here traveled in a straight line. So we can be certain with this experiment, we can be certain that cathode rays travel in a straight line. So with this experiment, actually J.J. Thomson, who carried out further experiments into our cathode rays, actually conducted this experiment and discovered the fact that cathode rays are traveling in a straight line. These invisible particles or invisible radiation that is produced from the cathode was actually traveling in a straight line. And that was proven by placing this opaque object along the path of the cathode rays, and noticed that it casts a shadow in the exact shape of the object placed in front of the cathode rays. Now let's move on to our next experiment. Students, we have in front of us a cathode ray tube with a paddle wheel inside of the tube. So we can see here inside this cathode ray tube we have a set of rails made out of glass, and on those rails we have a very light metal pedal wheel. So as you turn on this cathode ray tube, as cathode rays are being formed, and when they are trying to travel from the cathode towards the anode, along their path you have the pedal wheel. So the cathode rays will come into contact with the pedals of the pedal wheel, and we are going to observe that the cathode ray particles, or whatever the particles that are emitted by the cathode, actually has kinetic energy. We are going to observe that the cathode rays have kinetic energy by observing that this pedal wheel are starting to move when we turn on the cathode ray tube. As the cathode rays are formed when they travel from the cathode to the anode, we are going to observe even the pedal wheel is going to start spinning and travel from the cathode to the anode. And if you switch the cathode and the anode by turning this knob that we have over here, we are going to observe the wheel will also start traveling in the opposite direction again from the cathode to the anode. So it will go from cathode to the anode along with the cathode rays. So this indicates that the particles that are emitted by the cathode had momentum or kinetic energy. So the particles that are emitted by the cathode actually had momentum or kinetic energy. So for example, if my right hand side, this particular electrode, let's say if that is our cathode, as cathode rays get formed from this side of the cathode ray tube, where they will try to travel towards the anode. And you can see the pedal wheel is over here. So when the cathode rays are formed from the cathode that we have over here and travel towards the anode, they come into contact with the pedal of the pedal wheel, and as these cathode ray particles hit the pedal will turn and it will start spinning and traveling towards the anode. And if I switch the cathode and the anode, you will see the pedal wheel will start moving in the opposite direction. So as this experiment is conducted, I'm going to keep switching between these two electrodes. I'm going to make sure that one of the electrodes is the cathode, and then later on, after a few seconds, I will switch it so that that becomes the anode and the left hand side electrode becomes the cathode. Now students, I'm going to turn the device on, and at this point the device is set up for this right hand side electrode to be the cathode, and you are going to observe this pedal wheel traveling from the right hand electrode, which is the cathode, towards the anode that is found on the left hand side of this cathode ray tube. So let's turn the device on. You can observe that the pedal wheel moved towards the right hand side. Now if I switch the two electrodes, you are going to observe the pedal wheel is traveling towards the right hand side. As you can see, when it comes onto the end of the track, it gets pushed back, but again it keeps on traveling towards the right hand side. But if I switch each time that it reaches the end of each track, you can see this pedal wheel keeps traveling back and forth. So as it goes from left to the right hand side, the left hand side is the cathode, and when it travels from right to the left hand side is our cathode. Now when I turn it again, you can see left hand side becomes the cathode. Now the right is the cathode. Again the left is the cathode. You can see now I will turn the right hand side to be the cathode. So this is how you can actually observe. This is how you can observe that the particles that are formed in the cathode or at the cathode is actually having some kinetic energy. So now we have come to observe two main things, that the cathode rays that are generated at the cathode are traveling in a straight line. We observed it in the first part of this experiment, and on the second part of this experiment we observed these particles have kinetic energy, or the stream of radiation or stream of invisible particles that are traveling from the cathode to the anode has some kinetic energy or momentum. So that was observed by the fact that this pedal wheel was starting to move from the cathode towards the anode when we produced cathode rays. So students, with that part of our experiment, we can now move on to the next experiment. Now students, we have another type of cathode ray tube over here. Now this specific type of cathode ray tube is used to observe the path of the cathode ray. So you can see there's a metal plate that we have over here, and this is the cathode and this end is the anode. And you can see when the cathode is producing the cathode ray tubes, when the electrons are coming out of the cathode ray tube, according to the process that I mentioned in the previous part of this experiment, when these cathode rays are produced and when they are coming towards the anode, when they are moving in a straight line, they encounter this metal plate that will block the cathode rays. However, there is a slit in the middle of the metal plate that we have over here. Cathode rays cannot travel through such a thick metal plate, so this slit or the opening that we have in the middle will allow the cathode rays to travel through, and this will create a beam of cathode rays. So this cathode ray beam will be traveling in a straight line. As they travel in a straight line, they will come into contact with the metal piece that is placed inside the cathode ray tube at an angle, and this metal piece is coated with zinc sulfide, a fluorescent material. So when the cathode rays come into contact with this fluorescent screen, it illuminates. The areas that comes into contact with cathode rays will get illuminated, so the path of the cathode ray will be illuminated with this zinc sulfide fluorescent screen. If you take a look at the top view of this cathode ray tube, you will be able to see that this zinc sulfide screen is placed at an angle so that cathode rays, or the beam of the cathode ray that is taken into this middle section of the cathode ray tube, comes into contact with this zinc sulfide plate that we have inside the cathode ray tube. So students, this particular cathode ray tube is mainly used to observe the behavior of the cathode ray when subjected to a magnetic field and electric field. Now, before we start turning on the induction coil and observing the path of the cathode ray, you should know the cathode rays are traveling in a straight line. We have proven it. Even in this particular cathode ray, that will be very clearly observed. Apart from that, we know when subjected to a magnetic field, cathode rays will move perpendicular to the magnetic field. Cathode rays will not get attracted to either the north pole or the south pole of a magnetic field. Instead, cathode rays will move or will get deviated perpendicular to the magnetic field. If you have a magnetic field above and below, as cathode rays pass through the magnetic field, they will move in a perpendicular plane to the magnetic field and will get deviated due to the presence of the magnetic field. So we will observe that over here. And apart from that, we are going to observe what happens if you bring a negatively charged copper plate close to this cathode ray that we observe over here. So cathode rays are basically moving negatively charged particles. So, or we can say cathode rays are a moving beam of electrons. And as you bring a negatively charged copper plate, you would see that the cathode ray is deviating away from the negatively charged copper plate. So this indicates the stream of cathode rays or stream of particles found in cathode rays are negatively charged. Or in other fact, we do get the confirmation that the cathode rays are consisting of electrons, and electrons are negatively charged, so therefore they will get deviated away from the negatively charged copper plate that we bring close to our cathode ray over here. So students, let's move on to that observation. So first, let's observe how the cathode ray behaves in the presence of a magnetic field. We'll connect the cathode and the anode to the relevant electrodes, and then we will turn on our induction coil, and you can observe the cathode rays are traveling in a straight line. You can observe very clearly that the fluorescent screen is getting illuminated only in a straight line. So if you bring a magnet to it, a magnet has a north pole and a south pole, you will observe how the cathode ray changes its path based on how we introduce the magnet towards the cathode ray that we have over here. So the cathode rays are traveling like this. So if we bring the magnet at this angle, the magnetic field will be going in a straight line. So when I bring the magnetic field, you will see how the cathode rays are moving. So the magnetic field will be pointing towards the camera, and cathode rays are traveling in a straight line, right? So at that point, you can see how the cathode rays are not getting attracted towards the north pole. Instead, it is getting deviated in a perpendicular plane to the magnetic field. You can very clearly see this observation. Now, if I change the direction of the magnetic field, you will observe how the cathode ray behaves when we direct the south pole of a magnet towards the cathode ray. So the magnetic field is now forcing the cathode ray to deviate at a perpendicular angle to the magnetic field. Now, you can observe the same observation when we bring the magnet from the top. But now keep in mind, students, the cathode ray is traveling from my right hand side to the left hand side in a straight line. So when I introduce a magnetic field that is pointing downwards, the cathode ray will try to move at a perpendicular plane to the magnetic field. The perpendicular plane to the magnetic field at that point would be this plane that I'm indicating right now. So the cathode rays will try to turn inwards towards me. At that point, you will see that the cathode ray beam is disappearing. Cathode ray beam is disappearing because as it is getting deviated towards my direction, as cathode rays move towards my direction, you can see the cathode ray beam is disappearing when I bring the north pole towards the cathode ray. So the magnetic field is pointing downwards now. So at that point, cathode ray is trying to move at a perpendicular angle towards my direction. If I direct the south pole, cathode rays are now moving towards the camera or towards you, and you will observe the cathode ray beam becoming wider and trying to deviate at a perpendicular angle towards you. So it is not disappearing. Instead, towards the end of the fluorescent screen, you can see the cathode ray tube getting wider. Towards the end of the cathode ray, you can see the cathode ray getting wider. This indicates that cathode rays behave as charged particles behave in a magnetic field. During a magnetic field, as you may know, charged particles also get deviated in the presence of a magnetic field. The same way, cathode rays get deflected in a magnetic field. So let's observe one more time what happens when we bring the magnetic field in this particular angle towards the cathode ray. So you can very clearly observe how the cathode ray behaves when a magnetic field is applied to it. So when the magnetic field is applied in this particular direction, you can see the cathode ray is trying to move in a perpendicular plane to the magnetic field. The perpendicular to the plane to the magnetic field at this point is the plane that I'm indicating right now. So the cathode rays are trying to move in this plane. So cathode rays will come, get subjected into the magnetic field, and are now trying to move up. And then cathode rays will come down when the south pole is directed towards the cathode ray tube, like so. Now students, after making that observation, we can move on to the next experiment, where we bring a charged or negatively charged copper plate towards this cathode ray tube. So let's move on to that experiment. Now students, we are going to observe how the cathode ray behaves in the presence of an electric field. So we have here a negatively charged copper plate, and as we bring this negatively charged copper plate towards this cathode ray, you will observe how the cathode ray deviates. So cathode ray, when we turn on this cathode ray tube, you will observe the cathode ray is traveling in a straight line. When we bring down this negatively charged copper plate towards the cathode ray will get deflected away from this negatively charged copper plate. So this indicates that the cathode ray consists of a stream of particles that are negatively charged. We learned that cathode rays show particle properties, and cathode rays are traveling in a straight line. And now with this experiment, you are going to observe the fact that cathode rays are in fact negatively charged stream of particles. So let's turn on the cathode ray tube. Now you can see the cathode ray is traveling in a straight line, but as we bring this negatively charged copper plate, we will observe that it deviates away from the copper plate. As we remove it, it returns back to its original straight line path. However, if you bring this copper plate close to the cathode ray, we can observe that the cathode ray gets deflected away from the copper plate. As we bring it close to, you will observe, as we bring the copper plate close to the cathode ray gets deflected away from the copper plate. So students, you can very clearly see the cathode ray is no longer traveling in a straight line. This indicates that the cathode ray gets deflected away from this negatively charged copper plate, indicating that the cathode ray particles are negatively charged. In fact, we know that cathode ray is consisting of electrons, and electrons are negatively charged, and it will get repelled from this negatively charged copper plate. So that is why you can see the cathode ray is moving away from this negatively charged copper plate. Now students, this is the observation that I want you to make about how the cathode ray gets deflected away from the copper plate that is negatively charged. And after making this observation, we can now move on out of this part of our experiment. Now students, let's take a look at the summary of today's experiment. So in our experiment, we first started giving an introduction to this device. So we learned that this device is capable of doing mainly three things. It is capable of amplifying our voltage. So the input voltage would be around 230 volts, but it can be elevated all the way up to 10,000 or to 15,000 volts. And we learned that this device is capable of converting an alternating current into a direct current. Apart from that, with the use of a knob or a switch that we have over here, we were capable of switching the cathode and the anode between these two electrodes. After doing the introduction to this device, we moved on to our cathode rays. So all three of these tubes that I have in front of me are cathode rays that are used to show different behaviors of our cathode rays. The first tube that we have over here has a erasable opaque object inside the cathode tube or cathode ray tube. So this particular cathode ray was used to show that cathode rays are traveling in a straight line. We saw that when we connected the cathode of this cathode ray tube to the cathode of this device, we saw when cathode rays were formed, they were traveling in a straight line and later on casted a black color shadow in the exact same shape as the object that we have placed in front of our cathode rays. So this shadow that was casted in the shape of this exact same object indicated that the cathode rays were traveling in a straight line. Then we moved on to the second cathode ray tube. In this specific cathode ray tube, we observed that there is a pedal wheel inside the tube. So we use this second cathode ray tube to show that the cathode rays or the stream of particles that are found in the cathode rays have kinetic energy. So as the cathode rays gets formed from the cathode and moves towards the anode, we observed that this pedal wheel also started moving from the cathode towards the anode. This indicated that the cathode ray particles that were hitting or coming into contact with the pedal wheel allowed the pedal wheel to turn and move towards the anode. So kinetic energy that was found in the cathode ray particles were transferred into our pedal wheel over here, and the pedal wheel started moving exactly in the same direction as cathode rays did. So this particular experiment was conducted to show that the cathode rays are not simply a type of radiation without a mass or kinetic energy. We observed that the cathode rays are a stream of particles that had kinetic energy and momentum. So after observing the fact that cathode rays had kinetic energy in it, we moved on to the next experiment where we used this cathode ray tube with a fluorescent screen placed within the cathode ray tube at an angle, or we can say it is slanted, so that as the cathode rays travel from anode or cathode towards the anode, this slanted fluorescent screen actually comes into contact with the cathode rays, and since this fluorescent screen is coated with a fluorescent material like zinc sulfide, when the cathode ray comes into contact with this fluorescent material, you will see the fluorescent screen will get illuminated along the path of the cathode ray. So the cathode ray's path will be illuminated so that we can observe it. So when it comes to this particular device, we used it to observe how the path of the cathode ray got deflected in the presence of a magnetic field and in the presence of an electric field. In the presence of a magnetic field, we observe the cathode rays are getting deflected in the exact same manner how negatively charged particles get deflected. If negatively charged particles get deflected in a specific manner in the presence of a magnetic field, in the exact same way, you will observe the cathode rays are also going to get deflected. And then when we brought an electric field close to our cathode ray over here, we observed when a negative electrode was brought close to the cathode ray, the cathode ray got deflected away from the negative electrode. Cathode ray got deflected away from the negative electrode because the cathode rays were negatively charged. So students, this final test confirmed the fact that cathode rays are having a charge, and that charge is negative charge. So later on, with further experiments, J.J. Thomson identified that these cathode rays that we observe here are actually electrons. After J.J. Thomson came across these observations, he further conducted experiments changing the type of gas inside these cathode ray tubes, and he observed the same observations. He realized the particles that are getting formed at the cathode did not depend on the type of the gas that was present or on the type of the metal used for the cathode. Then later on, he discovered that these particles that are emitted by the cathode are in fact electrons. With that, we can conclude today's experiment. Let's move on to questions and other important theory parts revolving around this experiment. Welcome back to the classroom, students. So in the first part of our experiment, we looked at the theory parts revolving around the cathode ray tube, cathode rays, and subatomic particles of an atom. And then we went into the lab and conducted a few experiments revolving around the cathode ray tube. So here in the third part of our experiment, we will be taking a look at a few questions revolving around experiment number 1. So let's move on to the first question. Investigation of cathode rays were carried out by, now there are a few names here, Thomson, J. Thomson, Sir William Crookes, James Chadwick, Henry Becquerel. You should remember their names. So J. Thomson, Sir William Crookes, James Chadwick, Henry Becquerel, they were scientists that were conducting experiments especially revolving around subatomic particles. J.J. Thomson was the scientist who discovered the electron, who was carrying out experiments with the use of, as you guessed, Crookes tube or cathode ray tube. And Crookes, Sir William Crookes, was the scientist who initially investigated the cathode rays. So he was the one who was trying to conduct electricity through a gas with the use of a high voltage between a low pressure gas. So he, since he discovered cathode rays, even the cathode ray tube was named after him. So we know cathode ray tubes are also known as Crookes tubes. So J.J. Thomson and Sir William Crookes are the ones who were carrying out experiments revolving around cathode rays. So the answer is A and B. And we have James Chadwick. James Chadwick was a scientist who discovered the neutron, and Henry Becquerel was the scientist who initially discovered the radiation phenomena. So these scientists did not engage in experiments revolving around cathode rays. So answer is A and B. Which of the following statement is correct? Cathode rays were attracted towards magnetic poles. Is this true, students? Which of the following statements is correct? Cathode rays are attracted towards magnetic poles. Is this true? This is not true. We learned that it is not attracted to any of the magnetic poles. Instead, they get deflected perpendicular to the magnetic field. Cathode rays are attracted towards the cathode in electric field. Even this is wrong. Cathode rays are negatively charged. Even the cathode is negatively charged. Would cathode rays get attracted to a negatively charged cathode? No. Since cathode rays themselves are negatively charged, they will get attracted to the positively charged anode. So this is incorrect. Cathode rays cannot be obtained by helium gas. That is also incorrect. Cathode rays can be obtained with any gas, and the mass to charge ratio of any cathode ray particle is identical. We learned these parts in our first session revolving around this experiment number 1. The trajectory of cathode rays can be altered by an electric field. So yes, definitely. Cathode rays are charged particles. If you bring an electric field to these charged particles, their path can get deflected. Actually, cathode rays, since they are negatively charged, they will get attracted to the positively charged plate or anode of an electric field. So this fourth statement is correct. Fourth statement is correct. But for good measure, let's take a look at the fifth statement as well. Cathode rays are emitted perpendicular to the anode. Cathode rays are emitted perpendicular to the anode. Is it true? Is it emitted perpendicular to the anode or perpendicular to the cathode? Cathode rays are emitted perpendicular to the cathode, not to the anode. So therefore, students, even this is wrong. So there's only one correct answer here, and that is answer or response number 4. So the correct statement out of the statements that are given here is just response number 4. Who determined the charge to mass ratio? Charge to mass ratio of cathode rays. We have James Chadwick, John Dalton, Niels Bohr, J.J. Thomson, and Millikan. Now, out of these scientists, we know there was only one scientist out of the scientists that are given here who actually conducted experiments revolving around cathode rays, right? That is J.J. Thomson. If there was Sir William Crookes, then we would have had 2 scientists who were carrying out experiments revolving around cathode rays. So there's only one person here who actually conducted experiments associated with cathode rays. So the answer should be that J.J. Thomson. But apart from that, students, you should remember J.J. Thomson was the scientist that mainly carried out investigations associated with the cathode rays. And later he found out charge to mass ratio of cathode ray particles and was able to actually discover the electrons through calculations that led to the charge to mass ratio of cathode ray particles. So the answer here is J.J. Thomson. Millikan, of course, contributed to discovering the charge of electrons. So over here, Millikan also has played a role in identifying the charge of electrons. However, the discovery, the honor of discovery of electrons, as well as the honor of finding the charge to mass ratio of cathode ray particles or electrons, goes to J.J. Thomson. Answer is number 4. What is meant by a cathode ray particle? Is it an H plus ion? Is it an X-ray? Is it electrons emitted when atoms undergo ionization? Is it helium nucleus? A particle that is equivalent in mass to an electron. So students, we learned within the cathode ray tube, we have 2 electrodes that have a really high potential difference, and within the cathode ray tube we have gases that are at a low pressure. And we learned that these gases are moving randomly, and sometimes they can come and collide with the highly negatively charged cathode. So cathode is highly negatively charged, and as an atom comes into contact with the cathode, atom has electrons in the outermost margin of atoms. So these electrons, when they come into contact with the cathode surface, electrons of the atom can get repelled immediately. So this repulsion is going to cause an electron from the atom to immediately be removed from the atom perpendicular to the cathode. So this is what is known as our cathode ray particles, basically electrons. From where did these electrons come from? They came from the atom that came into contact with the cathode. So how were these electrons formed? By the ionization of atoms or molecules or gases that are present in the cathode ray tube. So the answer here is going to be electrons emitted when atoms undergo ionization. Yes, electrons do get emitted. For example, if you have a helium atom that comes into contact with the, let's say this is the cathode. If this is the cathode, if a helium atom comes into contact with this cathode, we will see immediately an electron will be shot out of the atom. So helium will turn into helium ion and an electron will be removed. So these removed electrons, this will not happen only once or twice every now and again. It will happen quite frequently within the cathode ray tube. So a beam of electrons that are produced like this is what we know as our cathode ray. These are cathode rays. Or more specifically, this particular single electron can be considered a cathode ray particle. So the answer is electrons emitted when atoms undergo ionization within the cathode ray tube. Who discovered the electron experimentally? So I have mentioned this a number of times. Electron was discovered experimentally by J.J. Thomson. Electron was discovered experimentally by J.J. Thomson, and that is something you should keep in mind, students. Now there are a series of other names you should remember. Out of these names, the discovery of electron, the honor of discovering the electron is actually given to J.J. Thomson. Answer out of these names that are given here is J.J. Thomson. What is the incorrect statement regarding the cathode rays? They deviate in a magnetic field. So first of all, we'll highlight what we need to do here. Incorrect statement regarding cathode rays. They deviate in a magnetic field. Yes, cathode rays they do actually show deflection or deviation in their path when a magnetic field is introduced. It contains particles with a mass and a negative charge. Yes, cathode rays are particles with a mass and a negative charge. That is also correct. It travels in speed of light. Cathode ray particles, do they have speed of light? We say cathode ray particles roughly has a speed of 0.5 speed of light to 0.9 speed of light. So it is not going to be traveling in speed of light. It actually comes, it has a range of 0.5 speed of light to 0.9 speed of light. It is not going to have the same speed as speed of light. So it is somewhat slower compared to the speed of light. So this statement is incorrect. Let's take a look at the rest of the statements. Can display wave properties. Yes, cathode rays or cathode rays do display, or electrons do display, wave-like properties. And using the de Broglie equation, we can also calculate the wavelength of cathode rays. Equal to mass of an electron. Yes, cathode ray particles are electrons. So therefore, each cathode ray particle is equal to the mass of an electron. That is also correct. So the only incorrect statement here is the third statement. So the answer here is response number 3. Then we move on to the 7th question. What is not a property of cathode rays? What is not a property? They travel in straight line. They travel in a straight line. Cathode rays, they travel in a straight line. Yes, cathode rays, they do travel in a straight line. They are emitted perpendicular to the cathode surface. Very true. Yes, cathode ray particles or electrons that are released from atoms when the atoms go and come into contact with the cathode are emitted perpendicular to the cathode surface. The charge to mass ratio, sometimes charge to mass ratio is given as E divided by m or Q divided by m. The charge to mass ratio depends on the nature of the gas. This is incorrect. Right? J.J. Thomson carried out experiments and realized the charge to mass ratio of the cathode rays do not change with the gas that is inside the cathode ray tube. So students, charge to mass ratio does not depend on the nature of the gas. Can ionize gases? Can cathode rays ionize gases? Yes. As cathode rays travel, students, when they come into contact with gas molecules or gaseous atoms, when cathode ray particles or electrons, when they collide with these atoms or molecules, they can knock off some electrons or they can remove some electrons from those gaseous atoms or molecules. So this can cause an ionization. So yes, they can ionize gases. They can ionize gases. This fourth statement is also true. It has momentum. Yes, we have observed that cathode ray particles have momentum by placing a pedal wheel between the two electrodes or along the path of the cathode rays, and we saw the pedal wheel was moving. This was evidence that cathode rays have, or cathode ray particles have, momentum. Mass of cathode ray particle is, now students, a cathode ray particle is essentially an electron. We discovered the charge of cathode ray particle. Actually, R.M. Millikan discovered that. But before R.M. Millikan discovered the charge of a cathode ray, J.J. Thomson discovered the charge to mass ratio of a cathode ray particle. So if you know the charge to mass ratio and if you know charge, then using these numerical values you can find out the mass of an electron. So electron's mass was discovered to be 9.107 into 10 to the power minus 31 kilograms. Very small mass. You should remember this number. The mass of an electron is 9.107 into 10 to the power minus 31 kilograms. Now students, in this question they are asking the charge to mass ratio of cathode ray particle. So there are a couple of options that are given here. So charge to mass ratio of a cathode ray particle can be given in two ways. One is 1.759 into 10 to the power 8 coulombs per gram. And the next format is 1.759 into 10 to the power 11 coulombs per kilogram. So we have two answers here that can make you a bit confused. We have similar numbers, 1.759 in both situations. One has 10 to the power 11 and one has 10 to the power 8. So this is why you should remember these details very clearly. So in this particular question, the answers are all given in coulombs per kilogram. So in that case, the charge to mass ratio of an electron or cathode ray particle is 1.759 into 10 to the power 11 coulombs per kilograms. So the answer is number 1, 1.759 into 10 to the power 11 coulombs per gram. In the answer number 4, we have 10 to the power 8 coulombs per kilogram. This answer is wrong. This answer is wrong. This answer is also wrong. These answers are nowhere near the actual charge to mass ratio. However, this answer that we have highlighted here, 1.759 into the power 11 coulombs per kilogram, which is the same as answer number 1, is the correct answer. So very clearly remember that when it comes to charge to mass ratio, it can be communicated in coulombs per gram or coulombs per kilogram. If it is in coulombs per gram, it is going to be 1.759 into the power 8. If it is coulombs per kilogram, it is 1.759 into the power 11. Right. What could be the charge of cathode ray particle? Charge of a cathode ray particle is going to be the same as the charge of an electron, which is 1.602 into 10 to the power minus 19 coulombs. Again, these values should be remembered. 1.602 into 10 to the power minus 19 coulombs. So out of the answers that are given here, this is the only correct answer. So you can see there are certain answers that are given to confuse you, like 1.206 instead of 602. So I hope that you wouldn't get confused with those kind of answers and look for the correct answer among the incorrect answers. So the answer for this question is answer number 3. Which statement is incorrect? Which statement is incorrect? When it comes to cathode rays, they can move light with pedal wheel. So can they move light with pedal wheels? Yes. They can produce shadow with sharp edges when an object is placed between the electrodes. True, we observe this in our experiments. Cathode rays show both wave and particle properties. Yes, de Broglie equation confirms this. Cathode rays can get deviated by both electric and magnetic field. Yes, we observe that in the lab as well. Hydrogen, helium and oxygen. The cathode ray particles produced by these gases show an progressively increased mass. So this statement is wrong. We know no matter what gas you use in the cathode ray tube, the mass or charge to mass ratio or charge of the cathode ray particle or simply the mass of the cathode ray particle do not change, because no matter what gas you include in the cathode ray tube, the cathode rays that are produced are electrons, and electrons in any element or any gas is identical. Because of that, students, the mass of the electrons that are found in the cathode rays are not going to depend on the type of gas we use in the cathode ray tube. So this statement where it says if you use different gases, there are masses of the electrons that are produced or the masses of the cathode ray particles that are produced are different is wrong. Cathode ray particles will not have different masses regardless of the gas you use. So the answer here, they're asking which statement is incorrect. Actually, which statement is incorrect regarding cathode ray particles or cathode rays. So out of the answers that are given here, the fifth response is incorrect. Which of the following statements is the most accurate? Cathode rays are attracted to the north pole of a magnet. Incorrect. Cathode rays are not attracted to magnets. They are actually repelled by magnetic fields. So that is incorrect. Neutrons do not get deviated by a magnetic field. Which is true, yes, neutrons do not get deviated by magnetic field or electric field because neutrons are not charged particles. Only charged particles show deviation in their path when subjected to an electric field or a magnetic field. Neutrons are attracted to the cathode in an electric field. Are neutrons attracted to anything in an electric field? No. Neutrons are neutral. They are electrically neutral particles. They do not get attracted to any north pole or south pole of a magnet or any cathode or an anode. Electrons do not get deviated by magnetic field. That is incorrect. Electrons, of course, they do get deflected by a magnetic field. We saw that when it comes to cathode ray particles are electrons. We saw when cathode rays are subjected to a magnetic field, they do show a deviation that is going to be happening perpendicular to the magnetic field. Cathode rays travel faster than speed of light. Definitely incorrect. If the speed of light is c, cathode ray particles have a speed ranging from 0.5 c to 0.9 c. If the speed of light is c, the cathode ray particle speed range between these values. So this is the fifth response is also incorrect. So the only correct response here is the second one. Answer is 2. Which of the following statements is the most accurate? So we are trying to find out which one is the most accurate. Electrons have particle properties. True. Yes, electrons do have particle properties. We wouldn't say that it is not correct. Electrons show properties of negatively charged particles or negative charged particles. True. Yes, electrons show properties of negative charged particles. Electrons get attracted to anodes. Electrons show deviation in a magnetic field, so they do show negatively charged particle properties. Electrons do not show particular or negatively charged properties. That is incorrect. Electrons show both. That is important. Both particle and wave properties. So that is absolutely correct. Both properties are shown by electrons. All of the above are incorrect. Wrong. So out of the given statements, the most accurate statement here is the fourth one. Electrons do have particle properties, but again, this sentence or this particular statement is not complete. Electrons do possess both particle and wave-like properties. And then electrons are showing properties of negative charged particles. Yes, they do, but more precisely, electrons are negatively charged particles. And then electrons show both particle and wave properties. Now that statement is more accurate. Electrons show both particle and wave-like properties. So the answer to this question is 4. That is the most accurate. That is the most accurate. So out of the answers provided, fourth answer is going to be the correct response. Who determined the charge of an electron experimentally? Charge of an electron. Now, discovery of electron was done by J.J. Thomson. Idea was given by Stoney. And charge of an electron was found by R.A. Millikan through his oil drop test. So the answer to this question is R.A. Millikan. R.A. Millikan. So you should know these questions or these answers before even reading the names that are given here, but you can read the names and find out if there is a more suitable name here. But since we know very clearly the charge of electrons were found experimentally by R.A. Millikan. What is the mass of an electron in kilograms? Now, earlier on we saw a similar question to this. In that question it was asked what is the mass of a cathode ray particle. Now, cathode ray particle's mass was 9.107 into the power minus 31 kilograms. Now, cathode ray particle and electron is both the same thing. So, what would be the mass of an electron then? Same mass, 9.107 into 10 to the power minus 31 kilograms, right? 9.107 into 10 to the power minus 31 kilograms. That is the mass of an electron in kilograms. What is the charge to mass ratio of an electron in coulombs per kilogram? So students, we saw that charge to mass ratio of a cathode ray particle earlier. So again, cathode ray particle and electrons are both the same. So cathode ray particle and electron, they have the same charge to mass ratio of an electron, which is going to be 1.759 into 10 to the power 11 coulombs per kilogram. Now, if you are communicating the charge to mass ratio of an electron, that is going to be having a value of 1.759 into the power 11 coulombs per kilogram. If you communicate it with coulombs per gram, it's going to be 10 to the power 8 coulombs per gram. So over here, 1.759 into the power 11 coulombs per kilogram. If it is in coulombs per gram, it should be 1.759 into 10 to the power 8 coulombs per gram. So students, this is 1.759 into 10 to the power 11. This is 1.759 into 10 to the power 8. So you need to remember this. Don't confuse these two values. Right? So over here you can see there are two answers that are similar. This answer and this answer. Now, the first response is the charge to mass ratio if the value is given in coulombs per gram. And the fifth response is the charge to mass ratio of an electron if communicated in coulombs per kilogram. Since we are asked for the answer in coulombs per kilogram, answer is the fifth response. This is the correct answer. 1.759 to the power 11 coulombs per kilogram. Which of the following statements are incorrect regarding the electrons? So the first statement says located around the nucleus of an atom. Yes, electrons are found around the nucleus, not within the nucleus. So we can say in an atom, electrons are found around the nucleus. That is correct. This statement is true. Negatively charged. Yes, electrons are negatively charged. A stream of electrons have momentum. True. We placed a pedal wheel in a cathode ray tube and we saw the pedal wheel moving from cathode to the anode. So as cathode ray particles collide with the pedal wheel, some amount of kinetic energy of the particles were transferred to the pedal wheel. So that means cathode ray particles or electrons had kinetic energy. For something to have kinetic energy, they have to have a mass and a velocity. When they have mass and a velocity, they have momentum. So that statement is true. Mass of an electron is 1840 times greater. Now, as soon as you see this number, you might feel happy because this number is correct if this statement was stated in another way. Because when it comes to an electron, electron's mass is roughly 1840 times smaller compared to the mass of the proton. Compared to the mass of a proton, electron's mass is 1840 times smaller. However, this statement says electron's mass is 1840 times greater than the mass of a proton. That is why this statement is incorrect, right? So sometimes students, when you see this number, you will immediately go to that answer and think that answer is correct, in the sense this statement is correct. But if you actually take a look at the mass of an electron and a proton, you would notice protons are much heavier, significantly heavier than electrons. As a matter of fact, protons are 1840 times greater in mass than electrons. So this statement states the opposite of that. So this statement is incorrect. Electrons found in all atoms are identical. Now, that is true. Electrons found in all atoms are identical. Even J.J. Thomson observed this. No matter what the gas he included in the cathode ray tube, he saw the charge to mass ratio of the cathode ray particles were identical, denoting that the electrons that he discovered had the same mass and the same charge. Who proposed the idea of electrons? Idea of electrons were initially proposed by Johnstone G. Stoney. Stoney proposed the idea. Then J.J. Thomson discovered the electrons through experimentation. So physical discovery of electrons was done by J.J. Thomson, and R.A. Millikan found out the charge of an electron experimentally. So the idea of electrons, even the name electrons, was proposed by Stoney. Answer would be Stoney. Answer to this question is Stoney. What statement regarding the charge to mass ratio of cathode rays is correct? Charge to mass ratio of cathode rays is correct. Helium and hydrogen cathode ray charge to mass ratios are different. That is not correct. Whether it's helium or hydrogen or neon or any other gas, charge to mass ratio of cathode ray particles produced by any gas is always identical. Different than the charge to mass ratio of an electron. So charge to mass ratio of cathode ray is different than the charge to mass ratio of an electron. That is also incorrect. Basically, cathode ray particles are electrons and they are identical. Electrons and electrons and cathode ray particles are basically the same thing, right? Cathode ray particles mean electrons. So electrons charge to mass ratio is the same as the cathode ray particles charge to mass ratio. So this statement is incorrect because of that. Charge to mass ratio depends on the type of atom. No. The cathode rays charge to mass ratio depends on the type of atom. No. What type of atom, whatever the type of atom included in the cathode ray tube, the charge to mass ratio of the cathode ray particles produced are going to be identical. Hydrogen and oxygen cathode ray charge to mass ratios are the same. Finally, the correct answer. That is correct. Regardless of what gas you include in the cathode ray tube, the cathode rays that are produced will always have the same charge to mass ratio. The charge to mass ratio of each electron in atom is different. All the electrons in any atom is identical. All the electrons are identical. In any atom, any element, all the electrons are identical. So therefore, students, charge to mass ratio of any electron in any atom or any element is going to have the same value. So the answer here is 4. What can be considered as evidence for the particle properties of cathode rays? Particle properties of cathode rays. The deviation of trajectory in a magnetic field. Now, this statement, deviation of trajectory in a magnetic field, is evidence that cathode rays are charged particles, right? This is evidence that cathode ray particles are charged particles. That is not evidence that is suitable for showing that it has particle properties. This is evidence that cathode rays, not cathode ray particles, cathode rays are charged. Whenever cathode rays reflect in a magnetic field, that is evidence that cathode rays are charged. And it is not suitable for this particular question. The deviation of trajectory in electric field. Again, in an electric field, when the cathode rays deviate, that is a sign that the cathode rays are charged. And based on which direction they turn, whether it is turning towards the cathode or the anode, we can actually determine the cathode rays charge. As the cathode rays actually got deviated towards the anode and away from the cathode, this indicates that cathode rays are negatively charged. So this particular statement is not proving that cathode rays have particle properties. Produces shadow with sharp edges when an object is placed between the electrodes. So this shadow with sharp edges is an indication that the cathode rays are traveling in a straight line. So when you want to prove that cathode rays are traveling in a straight line, you carry out this experiment. And this is not an experiment that proves that the cathode rays have particle properties. Cathode rays can move a lightweight paddle wheel towards the anode. So when it comes to cathode ray students, they can move a paddle wheel from the cathode towards the anode. Now this is a clear indication that cathode rays have particle properties. So if cathode rays have a mass and a velocity, then as cathode rays are moving from cathode to the anode, they have momentum and they have kinetic energy. And when they strike the pedals, then some of this kinetic energy is transferred to the pedal wheel, and then the pedal wheel will start to move. So this particular experiment proves the cathode rays are actually consisting of beam of cathode ray particles. So cathode rays have particle properties. So the answer for this question is 4, but we'll see if the fifth statement also contributes or can be taken as an answer. Cathode ray can be produced by any gas. That has nothing to do with the particle properties displayed by cathode rays. Cathode rays can be produced by any gas. This actually is evidence that all the cathode rays that are produced are identical, and in all gases cathode ray particles are present. Cathode ray particles are electrons, so this is evidence that electrons are present in all the gases that you can include in a cathode ray. So the answer for the question number 20 is 4. Answer for the question number 20 is 4. So students, now we move on from the MCQs into a structured essay question. Let's take a look at the first question here. The ionization energy graph of element M is shown below. On the x-axis, we have the ionization energy number. So first ionization, second ionization, third, fourth, fifth ionization. So these are the ionization energy number, and these are the ionization energy values. So you can see these ionization energy values are communicated in kilojoules per mole. Now the first question is, to which group does M belong to in the periodic table? Now students, when you are provided with a graph such as this one, where the ionization energies are given to you or plotted in a graph and given to you, you can easily identify the number of outer electrons by observing the graph. When you are successively removing electrons from an atom, if these electrons are removed from the same energy level, the increase in ionization energies are going to be gradual. So you will see a gradual increase in ionization energies when you are removing electrons from the same energy level. However, if you are moving into an inner energy level and trying to remove an electron, at that point there will be a steep increase in the ionization energy value. So over here also you can observe a similar situation. Ionization energy number 1, first ionization, second ionization, third ionization. We can see a gradual increase of ionization energies, a gradual increase. And then all of a sudden, when you are trying to remove the fourth electron, there is a higher, steep increase in the ionization energy. This indicates that the fourth electron was removed from an inner energy level. Fourth electron was removed from an inner energy level. So these 3 electrons were present in the outermost energy level, and as you moved into the inner energy level, we saw a sudden increase in ionization energy value. So since we only have 3 electrons here, electron number 1, 2 and 3, so these are valence shell electrons. These are valence shell electrons. So these electrons can be used to determine to which group that element M belongs to. So we know there are 3 valence electrons in our elements that are grouped under group 13. So based on this, we can say that element M is found under group 13 of the periodic table, because all of the group 13 elements of the periodic table has 3 valence electrons, or 3 electrons in the outermost energy level. What is the most probable valency that M can have? Now students, in main group elements, whenever they are trying to remove electrons or gain electrons, they actually do so to obtain a noble gas electronic configuration. So we have in the outermost energy level only 3 electrons here. So if M wants to obtain a noble gas electronic configuration, the easiest thing to do is remove these 3 electrons. So the valency of this element is 3. We can remove those 3 electrons rather than gaining 5 electrons. It can remove these 3 electrons and obtain a noble gas electronic configuration, right? So because of this, when it comes to element M, the valency, since it has only 3 outer electrons in the outermost energy level, the valency of element M is going to be 3. M is not a transition element, and the atomic number of M is Z. So M has atomic number called Z. Will the first ionization energy of element Z minus 1 be greater than the first ionization energy of M? So this is a very interesting question. Now M is not a transition element, right? So that means M is a main group element. And then they say, when it comes to Z minus 1, if the atomic number of M is Z minus 1 element, what type of ionization energy, first ionization energy, would it have? Z minus 1 element. Will it be greater than M's first ionization energy, or will it be smaller? Now students, since M, we can see M has inner energy level as well, and therefore the outer energy level electronic configuration of M is going to be Ns2 Np1, and it's not a transition element, so we can write the electronic configuration of the outermost energy level of M like this: Ns2 Np1. It has 3 outer electrons, so this is the electronic configuration of just M. So after noticing this, if we are talking about Z minus 1 element, it will have 1 electron less than M. So electron configuration is going to be Ns2. We'll first write those down. It wouldn't have any electrons in the p sub energy level. And you would also know that when it comes to going across the periodic table, if you take a look at the second period of the periodic table, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Now, if you write the group numbers here, group number 1, 2, 13, 14, 15, 16, 17, 18. And there are 10 numbers allocated for D block of elements that are going to be observed from the 4th period onwards. This is the 2nd period. Right, from the 4th period onwards, we have D block of elements coming in. So for that, we have allocated 10 numbers. And if you take a look at the 3rd period, it is going to be sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Now, in these 2 periods, we actually can see a very clear trend in the ionization energies, first ionization energies. Actually, students, that trend is quite clear. So we'll first draw those 2 trends. We know if you take both of those trends, they will look quite similar. So we can draw them side by side. Now, students, if you analyze this first ionization energy trends across the 2 periods, in the 2nd period, we have lithium here, we have beryllium, boron, then we have carbon, nitrogen, oxygen, fluorine, and neon. These are the first ionization energy trend of period 2, and this similar trend can be observed in the 3rd period as well. Potassium, actually sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Now, in each of these trends, you observe that group 2 elements have a higher first ionization energy than group 13 elements. You can see this is group 1, this is group 2, boron is in group 13, group 14, nitrogen group 15, oxygen group 16, chlorine group 17, neon group 18. In the 2nd trend as well here, 1, 2, 3, actually not 3, it is going to be 13, 14, 15, 16, 17, and 18. In each of these instances, we can see group 13 elements. They have a lower first ionization energy than group 2 elements. So, according to our findings here. Element M is in group 13. It's in group 13. So when you have an element that has one less of a proton in it, or when the atomic number is one less than the atomic number of M, that falls into group 2. So we saw group 2 elements. Group 2 elements always have a higher first ionization energy than group 13. Group 2 elements always have a higher first ionization energy than group 13 elements. So the answer to this question is, will the first ionization energy of the element Z-1 be greater than the mass, greater than the first ionization energy of M? Answer is yes. First ionization energy will be greater in Z-1 element compared to element M. So answer will be yes. Explain your answer to the above question. Now, why is this happening? Why is the first ionization energy of Z-1 element is going to be higher than M? So let's say M, element M has Z mass, Z atomic number, and its electronic configuration, the outermost energy level is Ns2 Np1. And when it comes to Z-1 element, that has electronic configuration Ns2. So students, the answer to this question is here. The answer to the question is here. You can see, if you compare this outermost energy level electronic configuration of these both elements, when it comes to Z-1 element, it has a more stable electronic configuration. It has Ns2. The sub-energy level is completely filled here. The S sub-energy level, outermost energy level's S sub-energy level is completely filled here. However, when it comes to this element M, which is in the 13th group, has Ns2 Np1. It has only one electron in a P sub-energy level. So when you have only one electron in P sub-energy level, it's not a very stable electronic configuration. If the P sub-energy level was half filled or completely filled, then it would have been a more stable electronic configuration. However, this P sub-energy level is just containing one unpaired electron. So this is not a very stable electronic configuration. So removing an electron from such an unstable or relatively less stable electronic configuration like this is going to require a lower amount of energy. And over here, Ns2 electronic configuration is relatively more stable compared to Ns2 Np1 electronic configuration. Why? Because we have a s orbital that is completely filled in the outermost energy level, and we don't have any other electrons in any other energy levels or any other sub-energy levels. So therefore, in the outermost energy level, the S sub-energy level is completely filled here, which is a stable electronic configuration compared to the electronic configuration that is seen in element M in its outermost energy level. Outermost energy level of element M has a unstable electronic configuration, Ns2 Np1. When we say unstable, students, this is compared to element Z-1. So therefore, removing of an electron from this place where there's only one electron in P sub-energy level is going to be easier. And removing an electron from relatively more stable Ns2 electronic configuration that is seen in Z-1 element is going to require more energy because this is more stable. So when you're removing electron from a more stable position, then at that point there will be additional requirement of energy. So energy required to remove an electron from this electron configuration is greater, and energy needed to remove an electron from relatively less stable electron configuration like ns2 and p1 is smaller. So that is why element M's first ionization energy is going to be smaller than element Z-1's first ionization energy. So I hope you have understood the answer to this question. Let's move on. Write the electronic configuration of element X with the atomic number 17. So which element has the atomic number 17? Element with the atomic number 17 is chlorine. It has atomic number of 17. So we have to now write its electronic configuration. 1s2, 2s2, 2p6. By now we have completed 10 electrons. Then 3s2 and 3p5. Now all of you should be quite okay with writing electronic configurations that are simple as this. So this is the electronic configuration of chlorine. If M, in the previous part of this question, if M has an atomic mass that is smaller than 16, draw the dot cross diagram for the compound that can be formed between M and X. Note, when drawing the dot cross diagram of X, showing the valence electrons of each atom is sufficient. So if you take a look at the elements that fall into group 13, we know M is found in group 13. So these are the elements that are found in group 13. And in the question it mentioned that element M has atomic mass that is smaller than 16. And we know oxygen has atomic mass of 16. So that could be an element that appears before 16 or before oxygen. Oxygen is 16, nitrogen is 14, carbon is 12, and boron is 10.8, sometimes rounded off to 11 in certain periodic tables. So it has to be an element that is to the left of oxygen, and that has to be an element in the 13th group. So then we only have this option, which is boron. It can't be aluminium because aluminium has a atomic mass of 27. This question says the atomic mass should be smaller than 16. So the only option we are left with is boron. Boron is the only option that we are left with. So not oxygen, not nitrogen, not carbon. It has to be an element in the 13th period. That has to be boron. After identifying that and after realizing actually X is chlorine, after realizing X is chlorine, we can now think of what type of molecule we are talking about here. This is molecule formed between boron and chlorine. And we are asked to draw the dot cross diagram for BCl3, because when you combine, now boron has a valency of 3, chlorine has a valency of 1. So when you are trying to form a compound between the two, the formula will be BCl3. So we can first draw boron's dot cross diagram. So boron has 3 electrons like so. We can draw them like this. Each chlorine atom has this many electrons around it, actually 7 electrons around it. So valence electron number of chlorine is 7. We can display it with crosses since we use dots to display the valence electrons of boron. So then when you are drawing BCl3, we can draw that this way. Each unpaired electron of boron is going to pair up with the unpaired electrons seen in chlorine. Now chlorine has 3 lone pairs and 1 unpaired electron. So if you draw chlorine here, each chlorine has 3 lone pairs of electrons and 1 unpaired electron. And that unpaired electron is going to pair up with boron's unpaired electron. So this can happen 2 more times. This can happen 2 more times, producing BCl3. So this is the dot cross diagram. This is the dot cross diagram. So this is the only answer to this question, because this question asks us to draw the dot cross diagram. But there are Lewis dot diagrams as well. So if you are asked to draw Lewis dot diagrams, you can use only dots. So you can draw the Lewis dot diagrams in the following manner. Each chlorine should have 7 outer electrons, and 1 unpaired electron of chlorine is going to pair up with 1 unpaired electron of boron, which is going to look like this. You can see each chlorine has 3 lone pairs of electrons and 1 pair of bond electrons. This is a Lewis dot diagram, and this is a Lewis dot dash diagram. You should know how to draw all 3 of them. Although this question only asks you to draw Lewis dot cross diagram, you should know how to draw all 3 of these different dot dash, dot diagrams and dot cross diagrams. So students, if you have written the last 2 diagrams, that is not what is required by this question. So keep in mind, you need to only draw this answer. Now let's move on to the next question. So we see here a question about adding the above compound that we saw into a test tube containing methyl orange and iron powder. The above compound is added to the test tube shown below. Write the 2 changes that take place in this experiment. So we have methyl orange, students, that is an indicator, and we have iron powder. So when you add BCl3 to water, in this case we have methyl orange aqueous solution. So when you add it to water, it will form boric acid, H3BO3 and HCl. So students, boric acid is a weak acid. This is weak. This is a strong acid. This is a strong acid. Now students, there are 2 acids produced here, one weak, one strong. Either way, since acid is added to the medium when BCl3 actually reacts with water in the medium, BCl3 is reacting with the aqueous medium to produce boric acid and HCl. So when water and BCl3 reacts together, it will produce boric acid and HCl, and this is going to be a weak acid and this is going to be a strong acid. And since 2 acids are coming into the medium is going to turn acidic. And methyl orange, if if you take methyl orange, it shows different colors based on the medium or pH value. Based on the pH value of the medium, you will observe different colors for methyl orange. So we will draw a small table here to show the pH values of different indicators, common indicators that we come across in the lab, like methyl orange and phenolphthalein. I will take those two. So if you take a look at the pH or the color of different indicators in different pH values, over here we can take the indicator methyl orange, and we can take phenolphthalein, and then we can see the color of those in acidic medium and basic medium. Although we just generalize and write acidic and basic medium, students, there are different pH ranges that they show these colors in. So keep that in mind, but this is just a generalization just to give you an idea. When the medium is acidic, methyl orange will show a red color. And when the medium is basic, methyl orange will show a yellow color. When the medium is acidic, actually phenolphthalein at that point will show no color. It will be colorless. But in basic medium or alkaline medium, it will show a pink color. It will show a pink color. So when it comes to over here, students, methyl orange is still not present in acidic medium. It is going to indicate a yellowish color. And as we add BCl3 into this aqueous medium of methyl orange here, when we add BCl3 here, due to the formation of these two acids, the medium will be acidic. The pH of the medium will go down and the medium will acquire an acidic pH. In acidic medium, methyl orange will turn red. So one observation you can see over here is the methyl orange indicator will turn red. So this entire aqueous medium is going to turn red in color. And apart from that, HCl produced can react with the iron powder in this test tube. HCl produced can react with iron powder, and you can see the formation of gas bubbles as HCl and iron react. Hydrogen gas will be produced. Apart from that, you can see the iron powder will, the amount of iron powder will decrease. As iron reacts with HCl, it will get spent. So you will see a decrease in the amount of iron that is present in the test tube. You will observe that iron powder will start to react with the acid, and therefore the observation is going to be the iron powder mass, or the amount of iron powder seen in the test tube of Fe solid seen in the test tube will reduce. Apart from that, another observation is gas bubbles will be formed. So they are only asking for observations. Over here, what I have written under the second point is not observation. Actually, this is a statement about what happens, but the observations are methyl orange. Actually, we can remove this as an observation. So the observations are these. You will see the methyl orange indicator will turn red. Amount of iron powder seen at the bottom of the test tube will decrease, and gas bubbles will be formed when you are adding BCl3 to this test tube. When you add BCl3 to the test tube, there are going to be around 3 changes that you can observe. First, since BCl3 when dissolved in water is going to produce 2 acids as I showed you earlier, and these are going to turn the medium acidic. So methyl orange color will change from yellow to red. So you can see that color change taking place. And then apart from that, the amount of iron powder at the bottom of the test tube will start to get decreased as they react with acids. And as this iron reacts with acid, you will see gas bubbles being formed as well. So these are the main observations you're going to make when you are carrying out this experiment. So that is the third and the final question that we have to answer in this part. So students, with that, we conclude the question discussion that was associated with experiment number 1. So by now, we hope that you have developed a good understanding of the theory parts revolving around experiment number 1. We learned how to handle a cathode ray tube. We learned how cathode rays are produced. We learned how to test for the different properties of cathode rays. And then we discussed many questions that will allow you to answer different types of questions when you are sitting for the exam and when you are faced with questions that is associated to experiment number 1. So now we can conclude today's experiment and move on to the next experiment.